ready to begin this webinar, and I think we can start. First of all, I want to thank you all, the presence and the interest in this event. I also thank to all the invited speakers and participants. I can see that we don't have all the people that is registered yet, but I believe they are getting in soon. So, but I suggest we start. We have about 220 registered participants from 30 countries. And thank you all for being interested in sustainable and digital building. The construction industry has nowadays many challenges and tools available in order to increase the sustainability of buildings, and this is what we want to discuss now. I thank the participation from the president of the Polytechnic of Leiria, Rui Pedrosa, which I will ask to give some words to begin the session.
Thank you, Florindo. Good morning to everyone. First of all, of course, I want to greet all of you and thank you all to participate on this webinar of an outstanding topic, the sustainable and digital building. In fact, it's impressive that the numbers that Florindo mentioned, more than 200 persons that registered to assist on this webinar. So welcome to this webinar, welcome to the Polytechnic of Leiria. Of course, I want to greet the director of the CDRSP, Professor Nuno Alves, and also say that once again, our research centers show here a strategic position in the digital building, which is in line not only with several R&D projects that we have, but also the investment that we did last year when we opened the Big Print Lab with all the conditions for the new challenge for additive manufacturing in construction, as well to be used as test bed for the industrialization of the 3D printing in construction. I want to greet the engineering Armando Afonso, which represents here the Engineering Professional Association, the National Engineering Professional Association, in Portuguese, Ordem dos Engenheiros. I want to greet all the organizing committee and to thank all the keynotes and moderators that will share knowledge with all of us. I want to thank the confidence of the Build Collab that are a key partner of this webinar. I want also to emphasize something that are in the website of this webinar, which is that the digital transformation of buildings is a key point to achieve the European climate goals and to reach net zero carbon buildings by 2050. As well, the idea that the building industry needs to search for use of sustainable materials, new building processes, such as the additive manufacture, the BIM and the digital twin methodologies. In fact, this webinar has a full alignment to the main topics that are associated to the European and national policies related with environmental challenges facing the planet, particularly those linked to the Green Deal and the digital transition agenda. Finally, I want to highlight the relevance of this webinar in the context of the huge environmental and climate challenges that we face in a worldwide level that are linked with utmost framework programs and agendas to transform Europe in a climate neutral continent, but also linked to all the resilient and the recovery programs for all the European member states. In line with this context, I must to say that inside the regional university network, the European University Alliance that are led by the Polytechnic of Leiria, in addition to main strategies associated to design of European degrees, short advanced programs, the RUN EU Discovery Program, which is a research agenda, we proposed the co-creation of 3 European innovation hubs, including the Future Industry and the Regional Sustainable Development European Innovation Hub, which is completely linked with this topic that we will discuss on this webinar. I want also to use this opportunity to give to all of you to think on a particular challenge, which could be the design of a short advanced program on sustainable and digital building that could be a unique opportunity for the upskilling strategy on this area of construction. To finish, I wish to all of you a full morning of discussion with a high impact to society. I really know that with this webinar, we will emphasize a strong idea that was highlighted during this pandemic context, which is that science and knowledge are global, with no borders, and is completely dependent of national and international networks that need more and more multidisciplinary contributes, co-creation contacts, and only with global science and knowledge networks will be possible to overpass these kind of global challenges, such as the climate changes. Thank you and enjoy the webinar, Sustainable and Digital Building. Thank you very much.
Thank you, Rui, for your kind words and good ideas. I will now ask Nuno Alves, the director of the CDRSP, to give some words, please, Nuno.
Okay, thank you, Florindo. Good morning to everybody. It is with a great pleasure that I can say also welcome to the Sustainable and Digital Building webinar. And as the Mr. President of the Polytechnic Leiria mentioned, a lot of challenge we are facing on that regarding mainly in this context the exploration of the new computer models, process and materials in order to manufacture a better future to the society. In fact, this web seminar is well aligned with the research strategy of the Center for Rapid Sustainable Product Development. As you know, this research center was rated with a maximum classification of the excellent by the Portuguese Foundation for Science and Technology, and one of the main research pillars is the sustainability, mainly regarding the exploration of the new building information models, as well novel process, sustainable process, and materials. And I would like to congratulate Florindo and all organizing committee of this webinar as well. Thanks a lot to excellent, outstanding keynote speakers, as well all participants. It's a great challenge. As well, it's also a great pleasure for me. Our ambition as a top research center on this area is to be well aligned with the research agenda of the European Union. As you know, a lot of projects that were engaged as well I hope during these seminars you can establish some partnership regarding maybe new research proposals, mainly in the context of the European Union. Thank you to all. Thank you.
Thank you, Nuno, for your words. Yes, it is important to be aligned on the European agenda. Now I will give the word to Armando Silva Afonso from Ordem dos Engenheiros. Please, Armando. You have to turn on your micro. Micro is not. Okay.
Okay.
Hello.
I hope it's okay. Okay, thank you. Good morning to everybody. Dear Dr. Rui Pedrosa, President of the Polytechnic of Leiria, dear Dr. Nuno Alves, dear speakers, dear participants, I'm delighted to be able to participate in this opening session of this webinar on topics that are so relevant today. In fact, sustainability and digitalization are two themes very dear to the engineers. A few days ago, I read a sentence by a well-known scientist and philosopher, Noam Chomsky, who said that humans can become an unavailable organism in the earth. I completely agree with him. Our planet has surpassed all its limits, and we are slow to wake up to this reality. Sustainability has to be an overriding objective in all our actions, and also in construction, of course, where we have a great challenge today. The construction has to be efficient in terms of resource and energy consumption, and buildings in their use phase even more so. I would even say that zero energy buildings are a thing of the past. We have to start thinking about the vital triangle of the sustainability for the humanity, which are energy, water, and nutrients, and in global zero buildings. Digitalization will certainly be an indispensable tool for us to achieve all these goals. Therefore, the theme of this webinar could not be more important today, and important and timely. I wish you all a good job and reaching conclusions. Thank you very much.
Thank you, Armando. Nice words from you all, and thank you. We have now more participants. We are on time. The agenda for today is divided in two parts. We have the morning session and the afternoon session. In the morning session, Professor Luisa Gonçalves will share, and in the afternoon we will have Artur Mateus. So we are on time. Let's start with the morning session. Please, Luisa.
So good morning. Again, thank you all for the presence and also the availability of the speakers to share their expertise with us and to enrich this webinar about sustainable and digital building that intends to be a forum of discussion, which I wish a profitable webinar for all. And after these inspiring words of the President Rui Pedrosa, Nuno Alves and Armando Afonso, we can start with the presentation of José Diniz Silvestre. José Diniz is an expert in life cycle assessment of construction materials and assemblies. He also assistant professor at the Department of Civil Engineering, Architecture and Georesources of Institute Superior Técnico of Lisbon University. And he also research of SERIS, Civil Engineering Research and Innovation for Sustainability. He participated in more than 20 research projects, coordinates a national project about the circular economy in construction and an international collaboration project focused on multi-objective optimization of construction materials and buildings. And their presentation is about construction of BIM for sustainable and circular buildings. So the presentation is about 30 minutes, and after we have 5 minutes of discussion. So, Dr. José Diniz Silvestre, so the floor is yours, or the internet is yours.
Thank you very much for the introduction. I think you can hear me well.
Yes,
Yes.
of course, very well.
So I would like to start by thanking, giving my compliments and my acknowledgement for the organization of this webinar, and especially to Professor Florin Gaspar for inviting me to participate in this important event, and with a very important topic and different topics that are now mainstream and are a main concern not only in the construction area. So it is a pleasure for me to participate in this as a speaker in this webinar. As it was already referred, my presentation is related with the contribution of building information modeling for sustainable and circular buildings. I will present mostly some research works and also some research results that we achieved in the research group that I coordinated in our research center at CERIS. The research group is named Positive Cycle and is focused on the life cycle assessment from the material to the building scale. And when we talk about life cycle assessment, usually it is related with the environmental life cycle assessment, and I will underline and highlight that later. But we can also talk about economic life cycle assessment. So it is more related with life cycle cost. And when we have a broader overview of the sustainable performance, we sum up to the environmental and to the economic dimensions, also the social dimension. I will not focus so much in the social dimension. The social dimension in our more technical, more civil engineering area can be related with the thermal comfort and other areas of comfort in the building use. But I think other presentations later on in this webinar will focus on the energy performance of buildings. So this is the structure of the presentation that I prepared. I will start with this topic that I was talking about, the environmental LCA from the product up to the building scale. Then how can we implement this kind of analysis, the environmental and the economic life cycle assessment in BIM to achieve, of course, eco-efficient buildings. Then how can we progress from this multi-criteria assessment to a multi-objective optimization of buildings? And finally, I will talk a little bit about the contribution of BIM for circular buildings. And then I will refer some steps that we are still taking to progress in the research in this area. So starting with the environmental life cycle assessment, the environmental life cycle assessment specifically of buildings, as I referred in the beginning, it has to be a combination not only of engineering, but also of other areas related with the environmental engineering. And most of the times we have multidisciplinary backgrounds for all the experts that work in these areas. So they can come from civil engineering and start being expert on LCA. That is my case, but we also have environmental engineers, mechanical engineers, architects. So there are a multidisciplinary and different ways to become an expert in this area. So during my presentation, I will refer that is an area with significant demand of data. So we need a lot of data to make this kind of analysis for a whole building. And that can be expensive, of course, because of the time to get or to create this data. It's also complex because we are not analyzing only a product. We are analyzing a building, a very complex infrastructure with different kinds of materials. And on that way, we need to collect data about the technical performance and also the environmental performance of each of these materials. And we have another difficulty because after the end of construction, after what we call the cradle to gate analysis and the production of the materials and the construction stage, we need to start working based on scenarios. So to extend the life cycle assessment after the construction of the building, we need to work on scenarios. And of course, these scenarios become more uncertain if we start talking about 10 years, 20 years, or even 50 years after construction. So it is very important in this complex environment to have strict rules. We have, in fact, European standards to make the whole sustainability assessment of buildings, including the environmental, the economic, and the social life cycle assessment. And for the materials and for the whole buildings, it's important to define the functional units, the system boundaries, also in terms of the life cycle stages that I will talk later, and the databases that we will consider to estimate the potential environmental impacts of each material. Then, at the end of the analysis, it's important also to estimate the uncertainty of the data that we used. This is not so easy, but at least we should check the sensitivity of the results for the options that we made during the study. This is very important. I will not present any example of sensitivity analysis today, but we do that in most of the studies that we complete in terms of environmental life cycle assessment. So talking about the system boundaries, our environmental life cycle assessment of the product or of the whole building can have different boundaries. We can consider different combinations of life cycle stages. The most frequent is the cradle to gate, where we consider the production of each material. Then we have the construction stage. Here we are already at the building level. And then we have the other life cycle stages until the end of life, so the demolition of the building. So it all starts with the evaluation of each material. I put here a construction material just as an example. So for the environmental life cycle assessment of each construction material, we need to identify the main production stages, including all the raw materials that are used in the production of, in this case, a lightweight concrete block. Then the mix of these raw materials in this case, and then the other stages until the packaging and the transport to the building site or the construction site that is already out of the boundaries of the production plant. So the idea is that we need to make this kind of study for each construction material. And of course, if we look at the whole building, we have a huge quantity of materials and construction systems. So it's better to rely on previous studies and of course, we have databases and we have environmental product declarations that we can use to accelerate our assessment of the whole building. So how we express the environmental impacts of each construction material? Based on the European standards, usually we consider at least these six environmental impact categories. So we can highlight here the photochemical ozone creation. This corresponds to the summer smoke. So we know that during the summer, sometimes in Russia, in China, even in France, sometimes it is necessary to limit the number of cars that can enter in the city, because during the summer we have the pollution from the factories and there is not sufficient wind to dissipate these gases, and the ozone accumulates at low highs, and it is necessary to decrease, to impose a decrease on the pollution. We have the global warming potential that is well known by everyone, and we can also have the acidification that also results from the emissions from the factories and can result on acid rains and also on the acidification of the water. So the other two categories are corresponds to the non-renewable energy, so non-renewable embodied energy and renewable embodied energy. So if we reach the environmental impacts of these construction material, we can find that most of the impacts are related with the production of the raw materials. We also have some impacts related with the packaging, but the manufacturing itself, in this case, is not so significant because it only corresponds to the mixing and transport inside the plant for this material. So these results from the studies that we had already completed with many Portuguese producers. So we already worked with more than 25 construction materials producers in Portugal. And that way we developed a database of environmental impacts for construction products, and including also an estimation of the construction costs for all these products. From the materials we we define also construction assemblies or building assemblies, because this is important for the design of buildings. And yeah, I started in my PhD thesis to estimate the environmental impacts of different external wall solutions. Raul Gomes was a PhD student that I supervised and focused on flat roofs. And I am also supervising Vera Durão, that on her PhD thesis, she is focusing on pitch roofs. So the idea is for us to have a compilation, a database of environmental impacts and costs, not only for construction materials, but for the building assemblies, in this case, for the envelope of the building, for the building assemblies that are more used in Portugal. Because in fact, to estimate the environmental impacts of the whole building, we need to sum up the environmental impacts of each material. So some of our studies, some of the studies that we made with Portuguese producers result in environmental product declarations that are available, for instance, in the DAP Habitat system, EPD system for Portugal, and other studies result on scientific papers that are already available, and I will provide you my contact by the end of the seminar, and I can provide you any results that you need. So it is very important in each country to develop these databases in terms of technical, environmental, and economic performance of each material and building assembly to make possible the evaluation of the whole building. For instance, in Canada, they are even developing environmental building declarations. So this corresponds to the evaluation of the environmental impacts of the whole building. So how can we combine these results with BIM methodology? First, it is important to introduce building information modeling as a methodology or as an approach. The idea is that in this model of the building, we can introduce all the information that we have about different elements of the building. I am not a BIM expert, but just to introduce you a little bit with this idea. And based on that, our model can be simple at the start of the design project, but can become really complex when we go to the construction stage or to the management stage or use stage of the building. So we can have in this 3D model all the information that we want. That can be really a huge quantity of information about the different characteristics of the elements of the building. So it is important that we can integrate also the life cycle assessment within the BIM approach or within the BIM tools or BIM software that already exists. So the idea is that that way we can accelerate the life cycle assessment. And of course, if we can provide this kind of analysis inside a BIM software, we have direct access to the bill of quantities at the design stage. We can add the characteristics, the environmental impacts of each construction material or building assembly. And that way, in real time, during the design stage, we can improve the environmental performance of our building, or we can decrease as much as possible or optimize not only the environmental performance, but also the environmental cost, the economic cost of the building. So this kind of integration is still mainly being at the research stage, but I will highlight some alternatives that we have in the market. So in terms of commercial tools, we already have, for instance, inside the Revit software, the Tally plugin. The Tally is a plugin for life cycle assessment, environmental life cycle assessment, with some interesting characteristics. In terms of limitations, it does not recognize all construction elements, so it has a very specific and limited number of construction elements that are recognized and for which it has environmental information. And in fact, it is an environmental impact database that considered a German database adapted to the American context, so to the North American context. And it is not possible for us to edit any information. So we have to rely on the information that is already in the database. Another alternative is the French software DevBIM LOD. It has a huge database of environmental product declarations from French producers, but is not directly integrated in BIM software. So the idea is that we need to extract the bill of quantities from BIM software and then use this tool to make the environmental assessment. In Portugal and Spain, we also have this specific BIM and LCA tool. So inside the SIPE tool and in the Archimedes model, we can make an LCA with a connection with our BIM model. In this case, based on a Spanish database and based only on carbon footprint and embodied energy. So based on this, we can conclude that these tools have some limitations, at least in terms of the database. We must rely on the data that is already inside the tools. We cannot change that. And there are also some research studies, but usually the research studies use a lot of tools to transform the bill of quantities in environmental impact. So they have to extract the data from the BIM model and then connect to a life cycle assessment database. So it's not a direct integration inside the BIM software. So it is really important to integrate the database that I already talked about in BIM objects. And the idea is, of course, to automate the life cycle assessment of buildings. So we try to do that in the PhD thesis that I supervised of Ruben Santos. I co-supervised. The main supervision was by my colleague, Professor Antonio Guiar Costa. And the idea was to integrate completely the environmental life cycle assessment and also the economic life cycle assessment that is considered in the European standards, in the EN 15804, integrate that inside a BIM software. So it was necessary, of course, first to define the formulas and the data that we need to make the life cycle assessment of the whole buildings. And since we have different needs during the design project, at the beginning of the design project and by the end of the design project, we have different needs and different detail in terms of the information we have about the materials, different levels of detail. Ruben defined two kinds of analysis: a streamlined analysis and a complete analysis with more data being considered for the whole life cycle of the building, and in this case, mainly for the cradle to gate stage. So in this specific paper, he presented how he developed the plugin to work inside Revit. So how he feeds the information about each material inside each BIM object. So the parameters that were necessary to define for the environmental and then for the economic assessment for each construction material. And then you can find here the results in terms of the environmental and the economic impacts of this building that is a tower in Morocco. So you have here the impacts for different life cycle stages from cradle to grave. And it was also possible to use the plugin to visualize which materials, in this case in terms of global warming potential, which materials contribute more to the carbon footprint of the building. In this other paper, he studied an office building in Netherlands, and as you can see, we can visualize for the streamlined analysis in terms of life cycle cost, and also in terms of carbon footprint and embodied energy, we can visualize which parts of the buildings contribute more to each kind of impacts. And on that case, during the design stage, in real time, we can replace the most the materials that contribute the most to the environmental impacts, for example, and that way we will make a real-time optimization of the environmental or economic performance of the building, which means that we are talking about the sustainable performance of the building. Just to refer another work made also in collaboration with Ruben and with Vera Durão that I already talked about. And the idea was to define which kind of databases and which kind of environmental indicators we should use depending on the design stage of the building. So this is the level of development. It can be related with the design stage that we are progressing in terms of the design of the building. And we can go from single indicators to all the parameters that I already referred in terms of environmental impacts. So it is becoming more and more important to make the environmental life cycle assessment of a building. You can see here many examples, and in some years, I believe it will be mandatory for any kind of building project to include a life cycle assessment. It can be, as you can see here, for the Netherlands. It can be at the building permit application stage, and to make possible this kind of analysis is really important to have this kind of plugin or the possibility to have this automatization of the environmental assessment inside the BIM tool or inside the same software where the building designer builds the model of the building with all the characteristics, with all the specialities. So I talked about environmental and economic impacts. This means that we can find some difficulty on deciding how we can weight each of these dimensions. So what is more important, the environmental performance or the economic performance? And we are talking about a multi-criteria assessment. So most of the times we have many environmental categories. We sum up the economic dimension, and we have to make a decision based on different dimensions of performance of the building, and that is not easy to define what is more important. So based on that difficulty, we tried to develop a joint project that is an ongoing project with some colleagues from the Budapest University in Hungary. And the idea is to go from the multi-criteria assessment to multi-objective optimization in order to avoid defining weights for each dimension of performance. So in this paper that is already available online, you can find a study in the scope of the PhD thesis of Benedek Kiss from Budapest University. And the idea was to create a structure to model a building, to extract the energy performance and the environmental impacts. And as you can see, it was not an easy work in terms of the number of tools that were necessary to use. So we didn't optimize in this case yet the number of tools that we need to use. So the ideal situation will be to use only a BIM software and plugins inside BIM, but in this case it was not yet possible. But we achieved these results in terms of the optimization of different characteristics of the building. You can see here. So to optimize all the dimensions of performance, including cost, energy performance, and environmental performance, we reached these characteristics of the envelope for Portugal and for Hungary. So it was possible to define the optimized characteristics for the envelope for each case, based, as you can see in this chart, based on the life cycle cost and on global warming performance. So we have here the solutions that are not dominated, non-dominated solutions. And based on that, we don't need to give weights to each dimension of performance. Yes?
You are finalizing.
Okay, thank you.
Now continue, but
okay. I will finish in a while. So finally, in terms of the contribution of BIM for circular buildings, I will start talking about a little example in the scope of the PhD thesis of Verena Goswin that I supervised. And in this case, we started using geographic information systems to estimate the environmental impacts of sustainable materials. So in this case, we compared a normal concrete mix with sustainable concrete mix with recycled aggregates and with fly ash replacing a part of the cement, in this case 60% of the quantity of cement, and we can estimate the carbon footprint for the transport for a construction work here in this case in Lisbon. And we can see that the production of materials, the impact carbon footprint of the production of materials in light blue decreases. And in this case, the transport increases because we are talking about recycled materials, or in this case, a sub-product, the fly ash. The importance of the transport increases. But with this study, it was possible for us to define the carbon footprint of the most sustainable concrete mix in any concrete plant in Portugal with different compositions. Also, in the area of circular buildings, I invite you to visit the website of this project, in which we are participating with the coordination of 3 drivers and funded by EEA grants. And the Circular EcoBeam project is focused in circular buildings, and we want to have a platform, in this case, a platform to manage and to make the environmental assessment of the buildings at the design stage, to optimize and maximize the circularity of the buildings, and then to have a digital twin platform to manage the building during the use stage, including a maintenance tool. In the assessment tool for the design stage, we will consider in a plugin inside the BIM tool that will make possible to do the streamlined LCA, the carbon footprint, the levels evaluation, that is the sustainable buildings assessment tool defined by the European Union, the circularity assessment, and the cost assessment. So you have more information not only on that website, but you can contact directly the architects Teresa Ferreira and Joana Fernandes to ask for more information about this project, and you also can contact directly with me. In another project that started last year and that I am coordinating, we will try to provide as much as possible environmental and economic information about the end of life of buildings. So to conclude and to close the cycle of the whole life cycle of the buildings. So here you have more information in this website, and we are identifying all the construction wastes and collecting information about the costs and the environmental impacts of the different disposal scenarios. The final slide. In this final slide, I just want to highlight that we are just starting. Today will be the kickoff meeting of a new project. It will be the REV at Construction mobilizing project with the coordination of Build Collab, that is one of the sponsors of this webinar. And sorry, this is still in Portuguese, but it's a huge collaboration of different Portuguese entities, more than 20 Portuguese entities in the construction sector, to increment the use of digital tools and also to consider the environmental assessment at the design stage of buildings or other infrastructures. So I will be available for any questions, and sorry to surpassing a little bit the time. Okay, thank you.
Thank you very much for this amazing presentation. I like it very much. And now maybe the audience have some questions. The opportunity to put some questions to José Diniz. So no one has any question? No? So I like this idea of of using GIS to make this comparison, environmental comparison assessment of concrete mixes, and to specialize in this impact. I have a question related with your plugin that we did. So the idea is to put all the information related with the parameters of the objects in this plugin to allow this comparative evaluation in terms of the impact environmental. So you have a patent of this plugin. Is possible to use it?
In this case, the Ruben has developed the plugin, and in his PhD thesis and in the research papers that we already published, you can have access to the all development stages, because he used directly the Revit API. So he made the code inside Revit without any additional programming language. But of course, is available to provide it as a Revit API. The question is that yes, in this case, the database that he used is also available, freely available, because it was based on environmental product declarations available at the European level. So they are all available. But in this circular BIM project, and also in our collaboration with the Build Collab, we want to progress a little more. So the idea is to use other programming codes, programming languages like Dynamo, for example, to be more flexible and to make possible the connection with the digital twin and with the use stage of the building.
Okay. So thank you. No questions. So
I think we have a question from João.
okay.
João
Yeah,
Moutinho.
please. Yeah, thank you, if it's possible. First of all, I would like to thank and to congratulate José for the great presentation. It was a very, very interesting presentation. For those who don't really understand the importance of life cycle assessment, it has been totally clear. Thank you for that. Just a quick question about the way that we think that life cycle assessment can be included in building evaluation and in the future in the built environment. Because for what I've seen in the slide where you're mentioning how countries are dealing with this, mostly I think that only public buildings are now mandatory or have a mandatory life cycle assessment. So do you foresee that we will soon in Europe and in Portugal in particular have the same type of requirement for all buildings? Because if we want to really to go for the neutral carbon neutrality in 2050, we should be starting by now having that type of concern, right?
Yes, that is a very important question, and it is even more important for countries, most of the countries in Europe, where we don't have a massive quantity of construction, but we can have a very significant quantity of rehabilitation interventions. So we can see, and I also consider that is the best option. So we can see the French case where they connected the environmental assessment to the energy certification system of buildings. And that way is a first step. It is mandatory from last June for all buildings, so and not only for public buildings. So for all buildings where it is necessary to get energy certification, it is also necessary to make environmental assessment with the environmental categories that they defined, and of course including the carbon footprint. So I think that is a very important first step, and I think that will be the faster way to implement that. And in the last revision of the energy directive for the energy performance of buildings, the European Union already recommended that the energy certification should consider also the carbon footprint and the embodied energy for the materials, not only for the energy use of the buildings. Because as soon as we starting having very energy efficient buildings, the materials, so the embodied materials and the embodied impact of the materials become more and more important. So not only for the new buildings, but also in all the energy retrofit interventions. So I believe that it would also be important that all the energy retrofit interventions that the government in Portugal and that the European Union funds to have this kind of criteria.
Excellent. Thank you so much.
Thank you. So, and now, thank you very much for the presentation, and that was amazing. So now we are going to listen Christoph Merkenbroek. Christoph works as a senior lecturer at Joping University Department of Building Engineering, and is also visiting lecturer at Reykjavik University. He has won several prizes for his academic work, namely in 2014, the Article of the Year Award granted by the International Journal of Collaboration, and the Best Paper Award at 2015 Nordic Construction Economics and Organization Conference. And the presentation is about can ICT like BIM change the production process? So Christoph can start.
Thank you, Luisa, for the nice introduction. And I think it's a bit hard to follow now, Professor Sylvester, in this after this outstanding presentation, and I hope I won't leave you totally disappointed. But there was something Professor Sylvester said in his talk, and he had a slide where he showed an iceberg, you know, and he showed what was under the waterline. The iceberg of BIM adoption. I think it was no, was it the iceberg? No, the BIM iceberg. And I'm more under the waterline with my research. So in the murky waters of companies trying to implement and adopt this technology in their projects, which would be like sort of a precondition for all this LCA to become a reality and for the advanced simulations and so on. We need the industry to sort of get this technology going at project and organizational level. So I'm doing more the soft social stuff in a way that needs to be ahead of sort of then actually implementing the or actually getting to the full use of all this ICT that and all the opportunities we have there. And so my talk today is entitled, "Can ICT like BIM change the production process?" And what I want to do with you now is basically share with you a bit what I've done in my research life so far. It's a bit shorter, my research life, than that of Professor Sylvester. I'm a bit newer to the game, and but I'll like to share with you what we are doing at Jönköping University. And first of all, I would like to introduce myself a bit for those who don't know me. I'm also relatively new to speaking in Portugal. Although this is just a webinar, I think it's best for me to introduce myself and say some words about that before I go on to talk about the research that we have done into BIM implementation in construction projects and also related to the production. And I brought for you some case studies and some findings that we had from case studies in both the Norwegian construction industry and in Sweden. And then I'll share with you some of the learnings that we brought back from looking into practical cases of BIM or of construction projects where people worked based on BIM systems inter-organizational between their companies and to create both the design and to support the production. Okay. So about me, yeah, I'm coming a bit from the practical side. So it is before I joined academia, I was working for around about 10 years in construction projects, and I worked amongst other for Hochtief construction a bit. That is the largest German contractor, and I used to work for 5 years in Istak, which is the largest Icelandic contractor. So I've been, around and worked on construction sites in different parts of Europe, and that is a bit of my practical background. And here I brought you a slide to show you some of the projects I've been working on. This is Iceland for you, and I've, for instance, been involved in building a cultural center in Akureyri in northern Iceland and on the east coast, and a primary aluminium smelter in Reyðarfjörður. That's and then I've also been involved in some projects in the Reykjavik city area. That was, for instance, a spa and swimming pool in a bit north of Reykjavik, and this is a Bauhaus supermarket, not a supermarket, a hardware store, steel frame building. And so this just to give you an idea that where I've been practically, and most yeah, and like I told you, I worked for contractors mostly. So in construction projects on the ground, and very concerned with operations and things like that. And this is a bit about my research background and where I work at the moment. I'm senior lecturer at Jönköping University since 2016. And I'm also teaching some classes up at Reykjavik University in Iceland. So I'm working both in Sweden and in Iceland, and my PhD is from Norway. It's a bit sort of, yeah, and I'm German for people who wondered. But I got married to an Icelandic woman some years back, and that's how I ended up in the Nordic countries. And so ever since, I'm sort of around in the different parts of the Nordics. And yeah, so that's a bit my background. And also information systems. My PhD is not in civil engineering, it's in information systems, which is and research discipline for those of you who don't know, that is very concerned with the organizational implementation of ICT, information and communication technology. So people studying how IT, so it's a bit, in some universities you will find it at the business schools, for instance, this discipline, and some universities you find it at the more technical departments next to the computer science departments. So it's a bit between computer science and business school. And you may ask yourself how some civil engineer like me ends up in a school like that. That was basically, or in a PhD program like that. That was basically, my idea was to learn about the implementation of new construction IT from people that have done that professionally for many years. And so it was a bit the idea behind this. And I graduated from there in 2014, and that's about my background. And yes, my research about in construction production, basically it starts with my PhD project, which was an initiative from the wood-based building industry in southern Norway. So it was part of a wider research program, and I got funding for my PhD project from West Agder County Municipality and the Competence Development Fund of Southern Norway. And the reason for them setting up this type of research was that they wondered about why it's actually so few companies working with timber frames and timber frame buildings and so forth succeeded actually in using this technology in their projects. And at the time, you see this project started in 2011. In Norway, people had already committed large resources to implementing BIM on the ground. And starts big for some of you who are more familiar with the Nordic countries. The National Governmental Building Agency in Norway, they had started demanding BIM use mandatory on public construction projects since then. So it was mandatory by 2010. And you possibly remember the large discussion about making BIM mandatory in the UK later. But there's like a 5-6 year time gap between the UK stepping this up as national demand versus what the Norwegians did. So there was all this wondering, yeah, now we threw all these resources at it. Yes, we have a national initiative, but people seem to be struggling on the ground to make this a reality in their organizations. And that was a bit the background I had when starting on my PhD. And so there was also some research early research surrounding this from Professor Linderoth, who's now my colleague in Jönköping University, actually. Became later friends and colleagues. And he at the time wrote that based on his research, when he was also doing like project organizational construction management type of research, And he basically argued that nobody really feels responsible for long-term investments in ICT at a project level. So he said it's basically in our projects we have a hard time finding someone who's actually sponsoring the IT systems and investing in the IT infrastructure in terms of servers and softwares and proper computers and at an inter-organizational project level, so that we get basically our systems to an optimal use in our project organizations. So there's a lack of commitment, investment, sort of, because what you get in essence is, in addition to your construction project, you get an IT project to start with. So before you can digitalize and work effectively with our digital tools, we need to have everything else in place for a construction project. And if you think about it for a bit longer, so if you think about, like, let's say small office buildings or smaller projects that have a duration of altogether, let's say 6 months. So where people want to have the project completed by 6 months, and you have an IT project in addition that has to go before the building project and so forth, then you basically are often also really finding yourself in time constraints and troubles like that, not only financial constraints. So yeah, basically that was a bit the background. So where I started, and the research questions I looked into my PhD was basically how can building information modeling support a more integrated practice in the wood-based building industry. I know the slide behind me has printed concrete on it, but I'm a bit looked into the production in the wood-based building industry and the opportunities of BIM for that part of the industry. And basically, as a starting point was to identify what is the current state of BIM adoption for integration in this part of the industry, and what are the predominant social, environmental, and technical barriers for the adoption of BIM in the industry, and what changes will be required with respect to work processes and interaction between the actors in the industry to achieve improved design information sharing in the projects. So yeah, that was the idea. And then the research design I focused there was like to conduct a couple of case studies. So in a sense, what I did was like look for rather typical construction projects executed by the wood-based building industry in southern Norway. That were case A and case B. That was a residential, multiple unit residential building, case A. Case B was a library construction project. And I contrasted that with a project from the general AEC industry, which was at the time touted to be Norway's lighthouse project of BIM use. So it was selected by Building Smart International to be, what do they call it? They gave it an award for outstanding open BIM practice. And so it was a national role model for everyone to look at for how people are supposed to be using BIM in construction projects. And so what I tried to do in my research design here was like looking, okay, how do the people and construction organizations in the timber frame building industry operate based on these IT systems versus the national role model project, where BIM was actually prioritized as a project objective, in addition to bringing it in on money and quality and cost and time. They actually said that outstanding BIM practice was part of the project, and they allocated funding and resources for that. So people had actually, in this hospital project, that was really advanced stuff. And we published an article about it. Yeah, so you might be able to publish it. I think I would have to deliver the reference later, but basically it was an example for effective BIM practice. And yeah, so this was a research design. And here's some graphical ideas, what we talk about. The residential building you can see is a multi-story residential timber frame building. And the library, some of you may have seen it because it was on the front cover of, I think, Archicad for some years. So if you have it, the software in the shelf, you know, you will see this library on the printed on front of it. So that was a bit like their role, their exemplar sort of example for Archicad to use on the box. And then this is a hospital building, and all three of them used some sort of BIM modeling throughout their design and construction period. And then basically it was a qualitative research design where we actually set up interviews with those people that were most hands-on, central to the BIM use in the projects. So in case A, there were interviews done with the client, with the architect, the structural, geotechnical, and fire protection engineers, and then also with woodwork specialists here, namely timber frame designers and a structural timber engineer. I was specialized on timber frame structures, and those were 10 interviews, and this is, you see, 10 years ago now, the case A. And then case B, about a similar setup and similar number of interviewees. And then in case C, we also ran interviews. That was, case C was this hospital. And then in addition to all that, to further validate this and look into the findings a bit deeper, I arranged for a focus group discussion with some BIM experts in Norway that included 2 architects, a structural engineer, and timber frame builders. And that was basically the data collection in that project. And what we found, what I found at the time in 2014, mind you, that they were actually basically lacking some guidelines for inter-organizational BIM work, leading to communication breakdowns in the projects. So they basically didn't really agree on how to facilitate the data exchange in their project. And then also there's some special information needs in wood-based building production that are different from maybe other types of projects. So for instance, they used robotic CNC mills in production. So you would need to have some additional knowledge about that, even if you think about you know, they, like both of the companies, case A and B, that were central at the study, or the focal timber construction companies, they basically had robotic mills that could be basically model controlled, and but that knowledge hadn't made it to the design team. So the design team, both the structural engineers and the architects and all those people involved around it, they didn't have a clue what type of information was required to actually operate robotic mills. So the design wasn't taking that into consideration, and there was a lot of design, a lot of shop design and so forth left, and modeling left for the timber frame producers, manufacturers themselves. They basically said they need to take it all from the start So they got the designs from the architects and the structural engineers and couldn't use it to, to produce effectively. So basically what they had to do is scrap it, no, not totally scrap it, but redesign it to such a high degree that the design work was basically overall, rather inefficient. And so rather than having integrated information sharing and this cycle that also Professor Sylvester was showing in his slide, like where you have integrated practice and information seamlessly going between the different disciplines and further to manufacturing, that didn't seem really to be the case, that went down conveniently for anybody, and then you also need more better defined BIM contracts. And those also need to take into account the particularity of the type of building project you're actually dealing with and the way in which it's manufactured. And yeah, and basically this was in 2014. You might say it's old news, but I brought you some, I don't know, let me finish this off with this conclusion slide and then go to a bit more fresh stuff that we did do more recently. And so I came up with a theory, the grand theory of it all after this PhD project. And I basically found that we struggled basically fundamentally with this sequential, I mean, it's, you won't be that surprised by this finding, but we seem to struggle a lot with the sequential production process in our projects. So the traditional process that you have an architect meeting up with a client in the beginning of a project, then you get a bit later the structural engineers and the specialist designers involved, and then you have a tendering process happening and tendering the construction work, and so it's not happening at the same time. And that had an effect on the use of ICT systems in the projects. So you see that when you're in the very early stages of construction project, you could basically freely choose and pick your IT and your design systems. Like the architects were always happy. So if it didn't matter like which case study, you talk to the architects and they were happy with how it went down and how the systems worked and how everything was convenient, because they're early, they're at the start, they get to pick their software, and then those that follow after, they're sort of constrained, increasingly constrained what others have done and what they've used. And if you were in the manufacturer, you sort of there was a sort of some more desperation there. So they were very constrained with what they actually could manage to do and what type of software was, working for them due to what others had produced before. So there was like this bit, I call it the freedom of enactment. I still need to bring it into a great big journal, but it has been conference paper. I'm still trying to think about it, how this could become a major theory of construction IT, but I hope I can get tips from the audience later, but this is just something I was thinking there. So then I made some more work more recently, and here we looked into augmented reality and how that could be successfully applied to support here a very particular practice in wood-based production, that is the quality insurance in manufacturing. And there are a lot of great examples from other parts of the industry, like you will find Volvo and Bosch and Lockheed Martin and Boeing and all of those people having started to use AR and in conjunction with modeling for their quality control. So that was a bit inspired by their experiences. We actually did a so-called DSR. I explain in a second what I mean by DSR, a quasi-experiment in a Swedish prefab housing manufacturer. And DSR is basically the so-called design science research method for like that I bring from information systems. Remember, I told you that I was having a PhD in information systems, and there people use this. That is, if you basically have a new IT, like you have they call that artifact in that realm, and then you evaluate it with your users, and then you sort of have this design cycle where you design it and you evaluate it. But that, of course, happens in an environment where you have an application domain of your IT. So in this case, it would be a timber frame manufacturing company, and they have particular problems and opportunities there. So they have already systems in place, IT systems that they have been using before, and they have practical problems in stemming from that production environment, and there exist opportunities. And ideally, any software that you make or any new software development will be relevant to solving a practical and real problem in the industry. So you need to create this so-called relevance cycle so that the software or the solution that you provide will actually contribute to fixing a real-world problem there. And that ideally adds to the knowledge base. That is, if you want to get this type of work published, then you ideally have some new insights and experience, expertise, or scientific insights that you didn't have before. And so this is a bit what this research was based on, basically. And here we did a single case study. This is some photos from there, and we did basically I told you a quasi experiment. We did do some that comes on the next slides, but we basically had the quality inspectors in this timber frame factory work with HoloLens 2 devices, and we put the element design on the glasses with a Trimble Connect. And you're muted, Luisa. Luisa? Yes. Oh.
We are a little bit late, so it is important.
Yeah, I'm sort of used to 45 minutes speaking, Luisa. I'm so sorry. So I need to speed up a bit. Yeah, but I'll be at the end soon.
Okay, thank you.
And yeah, basically here we had sort of the production design or put on a HoloLens 2, and we had the quality inspectors, 5 of them in that factory. That was basically all of them using this in their inspection of the sort of the wall elements before they left the factory. And that was basically an early case study. Here you can see the basically data collection. So ahead of these studies, we needed to figure out what their real problems are. Again, this sort of we needed to figure out the environment in which this was to be used. So we needed to figure out, okay, how do they do their quality controls? How is the production line structured? How does this work, and so forth. Then we did do this first round with the production technicians and the quality managers and the so-called innovation engineers here. And then we basically brought the HoloLens loaded with the element data, and then we had this quality controllers, 5 of them, sort of use it in their practical work, and then feedback. We had this debriefing interviews with them after they have been using this HoloLens in quality inspection in the factory, and then we debriefed with them, and this is what we found. So they said that basically, and made it a lot easier to understand. For instance, pipe installations, color scheme proved somewhat, or color schemes proved somewhat effective in pipes. So, and then Microsoft HoloLens 2 is comfortable to wear. Yeah, they found that, and it's easy to spot the differences between the 3D model and reality, easy to spot deviations and mistakes, quick geolocation, makes quality inspections more interesting, is easy to use. Weaknesses, limited field of vision in the glasses, which could be a safety hazard, of course, in a production environment. It reduces attention to the wider work environment, requires getting used to and learning. Geolocation is not very precise. That was a sort of a bit both ways here. An exact model can never correspond to the imperfections of reality. And the data load up to Microsoft HoloLens 2 needs to be corrected. So basically here we're basically trying to really get the BIM models into the production world. So, and I've done some similar sort of research with steel fixing and, you know, reinforcement installations. So we had a case study, for instance, in Terminal 2 in Oslo Airport, where we looked into how the crews there used, but then we didn't have AR. They just used handheld devices and BIM models as opposed to drawings to basically do the quality controls and installations of difficult elements like elevator shafts and things like that were a bit more complicated in the practical aspects of reinforcement installations. So we did, so that's where my research is at. It's basically on the ground in the companies and trying to figure out what their problems are and what really is needed in terms of software to help them, for instance, here eradicate production errors in timber frame housing constructions. And they like the feedback is so that they believe by using this, they could streamline their quality inspections in a way that they actually could literally bring them to zero, the production errors. And that is promising, at least something to look further into. But then, you know, I owe you this, Luisa, to end. I owe you the answer to the question, can ICT like BIM improve the production process? Then of course, BIM is an absolutely wonderful tool and there's great potential to streamline costs on processes, to help different disciplines to communicate efficiently and to ensure little confusion on a job site. But to get to the promised land of benefits, you have to pass through the wilderness of adoption, which always seems to hinge on organizational change, not technology. And this is an inconvenient truth. And this Oakley, I think what he said in 2012 that didn't really change over the years, and I experienced that over and over. So you actually may find a lot of the stuff that I've seen in 2010 in Norway. You might just literally go out of the door and find a company that's struggling with the same stuff today. And so it's basically we also have in our industry, of course, the average size of a construction company in terms of staff is 2 persons, right? And so that can be a bit limiting when you think of advanced information systems and their use really throughout the supply chain. But that's a challenge, and we sort of need to find good ideas to work with that. And then also consequences of construction IT like BIM emerge over time. So if you implement it today, don't expect you know, results tomorrow. Or profit tomorrow. It's actually more, relatively costly to start up with new innovations for the companies. And I think you need a bit caution there. So sometimes you, for instance, see seminars where people say, okay, we're going to save 30% off this and that, and or we're going to be more profitable. And so that might actually mislead companies in their expectations. So it's, of course, you need to be realistic. If you change towards a new design system, you're going to experience some additional costs to start with, and there's some exposure there.
So, Christoph, is your final? Is you finished? Okay.
It's now finished, Luisa. So glad you asked. And do you have questions to what I've shared with you?
Thank you for your excellent presentation. So the next speaker had the necessity to get out at 11 o'clock. So if you don't mind, I think it is best to move on to the next presentation and in the end, we can make some questions about your presentation, if you don't mind.
Luisa, no problem. No problem. So the next speaker.
So, we need to move on. So the next presentation that will be presented by Francesco Asdrubali, that is a full professor of building physics and building energy system at University of Roma 3. They are participating in and coordinating several international research programs and is also author of more than 300 scientific papers and is also included in the list of Italian top scientists in the field of engineering. So, Professor, move on to your presentation. Thank you.
Thank you very much, Luisa. So the title of my presentation is Life Cycle Assessment of Energy Efficient Buildings, Recent Trends and Future Perspectives. My university, the University of Roma 3 in Rome, is part of a project of national interest on the renovation of existing buildings in NZEB Vision. It's a network of researchers from 12 Italian universities, and the work of my unit was centered on the cost optimality in the energy audit of existing buildings. What is NZEB? Well, I think it is well known to everybody, so I will go quickly through this slide. Of course, the introduction of NZEB buildings is promoted by various EU directives. And of course, these kind of buildings are very, very performant as far as thermal insulation, integration of renewable energy systems, and other plants such as heat pumps with high coefficient of performance. But the improvement of the energy efficiency during the use phase of this kind of buildings implies the introduction of extra materials, extra plants, renewable energy systems in the building, and this implies an increase in its embodied energy and embodied carbon. So there is a potential burden shifting from one life stage of the building to another. So from the operational stage of the building to the initial stage of the building, which means the construction. So the LCA approach, the life cycle assessment approach, is essential in order to avoid this burden shifting and in order to reduce the overall embodied carbon and embodied energy and the use of energy all through the life cycle of the building. The product category rules, PCR, indicates the various LCA stages to be included in the analysis. So we have a so-called upstream process, which is the product stage, the core process, the construction stage of the building, the use stage, and finally the end of life stage. So what generally happens with NZEB is that the use stage reduces significantly the consumption of primary energy, but there is an increase in the product and construction stage of CO2 emissions and use of energy. This is the definition of embodied energy. It's the initial embodied energy, which includes all phases from the extraction of the raw material until it is ready to be delivered to the manufacturer. Then there is the recurring embodied energy. It's the energy used in maintaining and repairing the building over its effective life. The total embodied energy is the sum of these two contributions. Similarly, there is the definition of embodied carbon, the initial embodied carbon and the recurring embodied carbon. The sum of these two contributions is the total embodied carbon. In order to evaluate the environmental effectiveness of NZ buildings and of the net retrofit of existing buildings more in general, two indicators are considered: the energy payback time and the carbon payback time. These indicators has to be included in the analysis as well as the economic payback time. The energy payback time is the ratio between the difference of initial embodied energy after and before the retrofit and the annual saved energy due to the retrofitting. Similarly, the carbon payback time is the ratio between the difference of initial embodied carbon after and before the retrofit and the annual carbon reduction due to the retrofitting. Both these indicators are expressed in years. Here there are some payback times found in literature works. We will see some more data in the following. Typically, solar systems have show very low payback times, while the substitution of windows or the insulation of the envelope of the building has much higher payback times. We conducted our analysis on various buildings. We started with the LCA of an ideal NZ building. So it's an ideal building of 6 per 6 per 6 meters dimensions, but it's on 2 floors with a certain transparent surface. This building was located in 3 different Italian cities, and it was simulated as an NZ with a flat roof with photovoltaic systems. And 2 configurations were considered: a reference building which was designed according to the Italian legislation on energy efficiency in buildings, and a higher standard building, an NZ building. I will go quickly through these slides. These are the different hypotheses. And for example, the building life cycle was supposed equal to 60 years. And these are the results. As you can see, in the standard building, the use phase is the red part, of course, is predominant, while the embodied energy is the blue one. It is not negligible, but of course, it is not predominant. In the NZ building, the use phase is reduced to 0. Of course, it is a building with a zero energy balance, but in this building, the embodied energy is predominant, is almost equal to 100%. For example, in Rome, in Fiumicino, in Rome, it was the embodied energy is equal to 94%. For this reason, it is essential to perform an LCA and reduce as much as possible the embodied energy in order not to cause a burden shifting of the embodied energy and embodied carbon from one phase to the other. These are the results of the life cycle analysis. The energy and carbon payback time for different solutions. As you can see, energy payback time are a little bit higher in northern Italy, where winter heating is really significant, but they are in all cases acceptable, lower than 10 years. So they are much lower than the useful life of the building and of the various components of the building. After this ideal case study, we studied a real building, a school in Turin, with the collaboration of the research group of the Polytechnic of Turin. And this is the school. It's quite a big, quite a large building, and we performed an LCA modeling, and I will go quickly to the results. These are the retrofit solutions. a cost-optimal solution, a so-called cost-optimal solution with an optimization of the costs and the benefits, a retrofit interventions in order to reach the current Italian legislation on energy efficiency, and two more performant retrofits in order to achieve the NZEB standard as defined by the Italian legislation. The two scenarios are called NZEB 1 and NZEB 2. This is a look at the life cycle inventory of all the materials included in the LCA analysis. And these are the results. The current energy consumption of the building without any intervention, since it's an existing building, is almost 160 kilowatt hours per square meter per year. With the different retrofit scenarios, we reach 40. So it is 1/4 approximately of the initial value. See, so it's really a significant intervention. And these are the results as far as payback times of the different scenarios. The economic payback time in the upper part of the figure, the carbon payback time in the middle, and the energy payback time in the lower part of the figure. As you can see, the cost-optimal, the so-called cost-optimal scenario is the best one, since it presents the lowest economic carbon and payback time. As we can see, a very, very performant scenario, the NZEB 2 has quite a long economic payback time, but the carbon and the energy payback times are quite low, approximately 5 years. So this means that the performant scenarios are good as far as energy consumption and as far as the environment, since they allow to, thanks to the savings in the operational phase, to pay back the investment in the construction of the building, in the retrofit of the building, in only 5 years. These are the results as far as different components in the retrofit, and according to other findings in the literature, the envelope insulation has a very long payback time, 30 years, while LED lamps, PV models, a biomass boiler, a heat pump, all of them have very low payback times in terms of 1-2 years, things like that. Some other developments found in the literature. These are the payback times of PV systems. Of course, there are very different data according to the climate, according to the technology and things like that, but we can see that all payback times are very limited for PV modules. They are lower generally than 5 years. Since the useful life of PV models is at least 25 years, there are at least 20 years of environmental and energy advantages in the use of these technologies. This is an English study, EU project Retail Pubs, bringing retrofit innovation to application in public buildings. And here we can see the results of this study, of this EU project. Payback times of the insulation also in this study were found higher than 25 years, while the substitution of the lamps, solar thermal panels and PV panels have very short payback times. This is a study from Hong Kong of a shading system. In this case, the energy and carbon payback times were found to be really very long, more than 40 years. And so this is something that we have to think about when proposing such kind of retrofit. This is another Italian study on different buildings of different construction periods. And here, payback times period were found quite short in northern Italy, while longer in southern Italy. As far as future perspectives, I think that dynamic LCA modeling is very, very important. What is dynamic LCA? It is an approach to LCA which incorporates dynamic process modeling in the context of temporal and spatial variations in the surrounding industrial environmental systems. It means that, for example, over the 60 years lifespan of a building, the energy mix of the country may significantly improve with a higher penetration of renewable energy systems. The efficiency in the plants or in the production of materials may significantly differ and, of course, hopefully be improved, and so on. So a stationary LCA is no longer representative in a world which is changing so quickly, with an ecological and energy transition, and with also climate, which is changing. So we have to simulate buildings in the next 50, 60 years, also according to different future climates. So this is the significance of dynamic LCA. We performed a literature review on the topic, and of course, dynamic LCA may be performed considering technological progress, considering different weighting factors, considering different emissions in the future, considering occupancy behavior of the building, which may change over time, and also, of course, climate change is another important factor. We studied an all-electric building, NZEP. This is an experimental building at the University of Trento, since we would like to study the effect on LCA of future energy mix scenarios. Since in Italy, the increase of renewable energies in the last 20 years has been really impressive. And so we consider that in future scenarios, the energy mix of the energy unit taken from the grid will be more and more made of renewable energies. So we model the building considering two future scenarios. Scenarios considering a limited decarbonization, and another scenario, it's the blue line, the blue trend, and another scenario which is characterized by a significant decarbonization. Of course, this has a significant impact on the operational phase of the building, and if it is an NZ, of course, with the zero energy balance, in a scenario with an important decarbonization, the energy savings are differently weighted compared to a scenario with a lower decarbonization. In other words, if there is a significant decarbonization, the CO2 saved is different, since the energy unit taken from the grid implies a lower CO2 emissions if there is such a scenario. This is the contribution to the total embodied energy of the different building components of our building, and this is the embodied carbon of the different building components. As you can see, vertical walls and the structure of the building in reinforced concrete have a significant embodied energy, but also PV modules, sorry, have a significant embodied energy and embodied carbon as well. This is the life cycle energy balance of the building: the embodied, the use stage, the end of life, and this is the life cycle carbon balance. This is the dynamic cycle emissions results. As you can see, without considering a dynamic LCA, we have only this starting point. Of course, this is projected throughout the life cycle of the building as far as the total global warming potential of the building. If we consider two different decarbonization scenarios, of course, the impact of the building during its life cycle decreases. And this is the effect of considering a dynamic approach in LCA studies. I will go to the conclusions, since I think my time is going to expire. The NZAP spread will increase the impact linked to the construction phase of the buildings, causing a shift of burdens. In the case study analyzed, the average increase has been determined to be equal to 26% for embodied energy and 19% for embodied carbon. The initial shift of burdens from the use phase to the construction one occurs only in the short term, since, of course, during the life cycle, the payback times are limited, a few years, and so during the life cycle of the building, the initial investment as far as embodied energy and embodied carbon is paid back. Some interventions, such as lamps and PV modules, have much lower payback times compared to other interventions on the envelope, such as thermal insulation and substitution of windows. Some interventions have a higher energy saving potential within the time frame considered in the analysis. The payback periods calculated are much lower. This is the most important result than the useful life of the building, confirming the important role on NZAP in addressing climate change and energy supply issues. It is essential to introduce as a future perspectives the dynamic approach in LCA studies. These are some of the papers referred to in the presentation, and I thank you very much for your attention.
Thank you for your excellent presentation. You have time to answer some questions of the audience? You are listening to me? Yeah.
Yes.
So any questions? I don't know if you have here any questions.
There were two hands raised, but they were...
I don't see. So if we have no questions, again, thank you so much. Okay, we have here from João. Okay, João, you can ask, you can put your question. You are asking, can I use energy
from the water movement
pipes?
Can you please explain how dynamic LCA can be beneficial in enhancing the retrofit and material for reduction of construction burdens in buildings? Okay. Dynamic, of course, we can see this from different points of view. For example, the approach of dynamic LCA is essential considering the maintenance of a building. It may happen that if we have to substitute some components of the building after a certain amount of years, in the dynamic LCA approach, we have to consider the real embodied energy and embodied carbon of that component, which is substituted, for example, after 20 years, in a different technological scenario. It may happen that that component is produced thanks to the technological improvement and the environmental optimization of the processes with a lower energy need and a lower carbon emissions. Of course, which is the importance of the energy mix as in our study. The energy and payback times are considered, are calculated considering the energy savings. But of course, the energy savings are not stationary throughout the life cycle of the building. When the building is constructed, let's make an example, the energy mix implies, for example, 200 kilowatt hours of CO2 per each kilowatt, 200 grams of CO2 per each energy unit taken from the grid. But this may happen that after 20 years, thanks to the carbonization, this value is reduced to 50 grams of CO2 per each energy unit taken from the grid. This means that we need higher payback times in order to recover the initial embodied energy and embodied carbon. So we can see dynamic LCA from different point of view, and it is important for an accurate future perspective of LCA studies. I hope I answered to your question.
So thank you so much. And now, and again, thank you for your presentation. So you need to move on and for the next presentation that are going to be presented by Dr. Biranci Panda, that is an assistant professor in the Department of Mechanical Engineering at Indian Institute of Technology, India. And he was also research associate in Singapore Center for 3D Printing. Is also associate editor of the Journal of Materials in Civil Engineering and received a Research Excellence Award from Singapore for his contribution to digital construction. His research focus is sustainable multifunctional composites and lies at the intersection of advanced manufacturing, material science, and multi-scale multi-physics modeling. Dr. Biranci, you can start your presentation.
Good morning. Yeah, nice to. So yeah, I'll just share my presentation, then I'll start it.
I can see it. We can see it, your presentation.
Okay. Yeah, I'm going to share it so that you can see it. Just a minute, please. I don't find any sharing option on my screen. Can you please help me?
But you can you have difficulties to share your presentation?
Yeah, exactly. Because I cannot find any sharing option on my screen. Yeah. Now I got it. Yeah. It's okay. Let me try. Yeah. Sorry. Yeah.
Okay.
Yeah. Is it visible now?
Yes.
Yeah. Okay. Fine. Yeah.
Fine.
Yeah. Okay. Very good morning to all of you. And thanks for invitation. So I'm Dr. Biranci Panda, assistant professor at IIT Guwahati, India. So currently I'm working on 3D printing of concrete materials, and my main focus is developing sustainable binders for this novel digital construction application. So today in this presentation, I'm going to share some of my work that I have devoted to develop sustainable binders for construction 3D printing application. So basically the motivation behind this digital construction is all about productivity in our construction industry. So if you see, compared to manufacturing, the productivity in the construction industry is quite stable over the years. And for that reason, it is very important to bring digitalization, which is among which concrete printing is one of the most important techniques which is getting attention from academia and industry in these days. So this is a just basic slide, like for those who are not from civil engineering. So it's I think everyone knows what is a concrete material. So how we do construction? So we do by creating molds and then pouring concrete into this mold box. So once this concrete is hardened, then we remove this mold box to get our concrete structures. So currently, if you see, there's a program from World Economic Forum. So they presented a scenario where the future of construction is going to be more automated and digitalized. So you can see very well from this presentation that 3D concrete printing is one of the most important technique which is going to highlight in the coming years. So exactly when I started my PhD in the back 2015, this concrete printing get lot of attention. Until today, many people in industry have been contributed a lot towards this technology. So this is a photo that I have found from a newspaper article that currently in the Japan, so a dam was constructed using a group of robots. So and they claimed by using this advanced robotic 3D printing system, they minimize the construction time up to 30%. Okay, so again I'm coming back to the main reason why we need to print concrete. So when I'm going to define why we need to print concrete, there are two reasons for me. The first is design freedom. So what does it mean to me? So means like in concrete printing, we can create a very complex structures without the need of mold. So as you can see this picture, it is from a French company X3. So they have printed this structure which is very complicated, and without the need of mold, they have directly printed it from a CAD model. So a second reason that is very close to my heart is sustainability. So what does it mean to me? It means that when you deposit concrete, so normally we do bulk casting. So more materials are being used in casting process. So what we can do in 3D printing, that we can optimize the topology and deposit the concrete where there's a need of materials. So this leads to sustainability because we can reduce the wastage of concrete. So these are the common two major reasons that is driving concrete printing in building and construction industry. So for me, I started my concrete printing research with this 3D printer. As you can see, it's a 4-axis gantry printer. It is connected with a controller, and the right hand side you can see a motor pump that has been used to deliver the material to the nozzle. So this is a very typical video of concrete printing. I hope there are plenty of video like this in the web. So you can see in this video that this concrete printing machine, which is a 4-axis gantry system, is depositing geopolymer concrete there. So now coming back to the material challenges, the first important criteria for developing 3D printable mix is to have a material that exhibits a very low yield stress during extrusion, so that we can extrude the material without any difficulty. But as soon as we deposit the material, it must harden rapidly to build more layers. But again, if you see that if you are going to make a very fluidly
Oops. Now we don't listen you.
Can you?
Dr. Biranchi, you are listening me? Huh. Some internet problems. Oh. Dr. Biranchi? Florindo, I think they...
I don't know what happened. It seems that it is having internet problems, in fact. Maybe if we take some time, I don't know if there was time for questions for Christoph. I don't know if anyone has questions. Maybe we can have some time now to discuss some points with Christoph, if we have it.
Yeah, if anybody remembers the talk, Florindo, so now 45 minutes ago.
Yeah.
No, but it was an excellent presentation and people remember it.
Thank you, Luisa.
I don't know if Biranci is still sharing the screen.
Yes.
Yeah. Well, actually, I have a question for Christoph. So you talk about mainly about your work, which is mainly related about wooden materials. And did you have some work in other materials also, or? Biranci is. Hello, Biranci. Hello, can you hear me? Hello, he's online. I don't know.
To deposit such nano.
Hello?
Yeah, sorry.
Biranci, we lost.
Am I audible?
No,
Yeah, I'm here. Hello.
Now we can hear you, but
I can hear you. Hello.
Hello, we can hear you now.
Yeah, I'm here.
But we lost the connection for some
now
time.
you can hear me. Okay.
Can you hear
fine.
me?
So shall I go back and start my presentation again?
Yes, you can, please.
Okay, fine. So I'll start the material research part. So
you have to share the screen, please.
Yeah, is it visible now?
No.
Okay, what I'll do, I'll stop sharing and start it again.
Yes.
Okay.
Okay, so I'll. Yeah, is it visible now?
No.
Just a minute.
Yeah, hello. Yeah, can you see?
It's starting. Yes, now it's visible.
Okay, fine. Yeah. Okay, so I'll start now. Thank you. Yeah, so coming back to the material research, so what happened, we started our concrete printing research with a very normal regular mortar, which consists Portland cement. And then because of this energy intensive of the cement production process, we started using fly ash in our mixed design. So as you can see, the fly ash is having spherical particles. And by adding fly ash with replacement of cement, we found the material with a very low viscosity, and ultimately because of this viscosity issue, we are not able to print more layers for the circular cylindrical shape. So after printing few layers, we found the structure was completely collapsed. So, and then we investigated different possible way to improve the buildability, and we found that nano clay is the best material for improving the texturopy as well as the yield stress. So as you can see in this graph, that adding a very small percentage of nano clay, the yield stress has been improved almost 3 to 4 times. And we investigated that there are so many reasons you can find in the literature that how this clay affects the yield stress. And we concluded in our research that due to flocculation of this nano clay modified mix, we are able to improve the yield stress. And due to that, we had a very good flocculation in our material. And if you can see this nano clay, they carry a negative surface charge and they're having positive charges at the end. So what happens during flow of the concrete, this negative charge, they repel each other, and we get a very flowable concrete, which is easy to extrude. But as soon as we deposit the opposite charges, they attract each other, they make a stiff material, which enable a very large scale printing. So I have divided the entire process into 3 reasons. One is the material at rest and during extrusion, and what happens after extrusion. So as you can see, the negative charges, they attract each other during extrusion, they repel, and again we deposit, they attract each other to make a very stiff concrete, and due to which we are able to again put more layers, which has significantly improved the buildability. So during printing, we measure the deformation and divide it into 2 types. One is elastic deformation, which happens slowly as you start printing. But after printing few layers, when the material stiffness exceeds the total weight of the concrete, plastic deformation happens and the whole structure collapses. So to measure the deformation in this process, we have added a laser sensor that controls this deformation, and it sends a feedback to the controller, and this controller, again, it was optimized with some parametric model that was automatically adjusting the print height so that the deformation can be minimized in concrete printing process. So again, one more important point that I would like to highlight during material development is all about texturotropy. So what is texturotropy? Normally, if you see when we squeeze the toothpaste, so it can easily extrude out from the tube. But as soon as we release the pressure, the material stays in its own position without any deformation. So this is something like texturotropic fluid. And for concrete printing, we need this kind of behavior. And if you want to characterize this behavior, in my research, I have done two tests. One is structural breakdown, and second is viscosity recovery to characterize this texturotropy. So we have used a geometer. We have applied a very high shear rate to completely break down the material, and we found an index called lambda, and this index is going to tell you how fast you can destroy your material, and it indicates that EG of extrudability, we relate structural breakdown to EG of extrudability. Similarly, we also characterize viscosity recovery. So what happens, like before extrusion, what is the viscosity and how the viscosity changes during extrusion and after extrusion. So, and this ratio we calculate to find the viscosity recovery ability of the material, and which is very important for us to deposit more layers. So now coming back to mechanical properties, we have tested both the materials, which is clay modified, and the control sample, we have found a better strength. And of course, clay is not affecting the structural structuration rate. So it means that clay has the potential to modify the initial material behavior, but it is not affecting the structuration rate of the material. So if you want to print a very large scale structure, means 3 or 4 meter, you still need to add some other chemical additives to improve the buildability. But the initial material fresh property can be modified with addition of nanoclay. So that was our conclusion. And to further accelerate the material hardening behavior, we have added some microsilica fume, and it has also a very good effect on texturotropy property. And by combining nanoclay, microsilica fume in appropriate percentage, we are able to print the 60 layers without any deformation. So if you refer to my first picture, we are only able to print 8 or 9 layers. But now with the modified mixed design, we have able to print 60 layers without any deformation. And of course, with addition of this microsilica fume and nanoclay, we have achieved a very good concrete properties. So yeah, coming back to another material development study. So in my PhD, the second topic was 3D printing of geopolymer. So here I have used a fly ash and GGBS combined with potassium silicate as activator. So in the beginning, I didn't change the raw materials like fly ash and GGBS. I only investigated the effect of this potassium silicate. So what I found that this potassium silicate is the main culprit, which is affecting the viscosity of the mortar. Because if you can see the viscosity of this potassium silicate, it is much more higher than the viscosity of the regular water that we use to make Portland cement based concrete. Again, this potassium silicate viscosity, it affects greatly with respect to its molar ratio or concentration. Okay, so as you can see that when I have a molar ratio of 1.8 and 2, it has a different viscosity, and accordingly the mortar viscosity changes, and with respect to the viscosity we have different shape retention of the material. As you can see that when I'm going to use a molar ratio of 2, due to high viscosity, I have a very good material stability. But in case of 1.8, due to low viscosity, the shape retention capability was not so strong. So then again, to improve the buildability, we use the same nanoclay with different activator to binder ratio, and also we change water to binder ratio. So the conclusion that we have derived from this study was that when we are using a higher percentage of potassium silicate as activator, it it has a more impact on the rheology coming when you are using the clay. So it means that clay cannot be used, even if it is being used with a higher dosage, it doesn't have much impact when you are using high volume of activator in formulation of geopolymer. So when the potassium silicate, that is the activator to binder ratio, it is below 0.35. So when we have a less activator, I will not say less activator, rather I will prefer to say when you have an optimum combination, then by adding some suitable additives like nanoclay, you can improve the buildability. As you can see that initially when we are printing without the nanoclay, we have deformation, and due to which after printing few layers, the stand-up distance was increasing significantly. But by addition of this nanoclay, there is no noticeable deformation of the layer height, so that there is no stand-up distance visible during printing. Again, the same rheological protocol was followed to measure thixotropy and characterize the shear thinning behavior of both the materials. And with the new materials, again, we tried to print a very small miniature structure with some 50 to 60 layers, and we printed without any deformation. And we found that the material that we developed, it has a very good thixotropy property, due to which we are able to print more layers without any structural collapsing issue. So this is a common video. I hope you can see it. We printed the complete geopolymer with a robotic 3D printing system. Yeah, so this project was a project sponsored by, it was not sponsored actually, we developed this fixed design for a competition that was organized by NASA. So they wanted to have a structure with a very less water amount. So we developed this material with a powder-based geopolymer. So it means all the activator that we have used, it was in the powder form rather than in liquid solution. So you can see that the structure that we printed, it is having a very good shape retention, and the layers are very pretty continuous, and it is, you can see that all the layers are continuous in nature without any deformation. So now coming back to, like, if you want to have large scale printing with these materials, then we investigated what are the causes and challenges that can be solved by R&D, so that we can print very large scale structures with our materials. So we found that when you are going for a very large scale printing, the material hardening is very important. You need to make such a material that rapidly hardens during printing. So which is completely depicted in this picture, that the yield stress of the material that you can use for measuring stiffness or hardening of your material can be one parameter, and with respect to time it need to be evolving, and depending upon the structure shape and the height, we need to fine tune this yield stress with respect to time. Then only we will be able to print large scale structures without any failure. So this can be done by two ways. One is like you make a very rapid hardening concrete, or you make accelerator kind of things by adding into nozzle directly. So it means you have two choices. One, by printing rapid hardening material, and second, you can still use a very long setting time material, but you need to inject some accelerator with the proper dosage at the nozzle. So you can see a similar configurations where both mortar that is coming to the nozzle as in one inlet, and the chemical additives, that is the accelerators, are being mixed at the nozzle, and printing can be done continuously for large scale structure application. Okay, so this is a typical common way to improve to print large scale structures. But again, we conducted some tests like green strength test and some shear apparatus test to find more information regarding material phrase property, because as everyone knows, in concrete printing the phrase properties are very important. So as you can see, like when the material is at a very fresh stage, we have a very load bearing capacity, and with respect to time, when the material hardens, we have a very shear failure in the material. So we conducted some tests with direct shear apparatus to find more material properties, and why this and how these material properties are important to us, because with this material property we can do some buildability simulation, and we can predict how many layers we can deposit for our materials for any large scale application. So this work we have done with collaboration with RMIT University. So they have developed some model with our material data, and as you can see, the model is able to predict the material failure very accurately. So this material data information predictability were used to now develop new materials that can be used to print large scale structures. So this was my part of the work for material development. Then I did some work on studying the process parameter, because as all of us know that in printing, any 3D printing process, material, process parameter and design, it all affects the print quality. So I have developed some algorithms to find what is the optimum print speed for your material with a constant flow rate. So for that, we started doing some research that what is the filament thickness, shape, stability with respect to different print speed, and we optimize it with respect to a model. So, and we found that when you are printing the concrete with different nozzles, it also affects the material property. As you can see, when we are using a very stiff concrete and we are using a circular nozzle, there is a lot of porosity in the material. But again, if you are using the same circular nozzle with a slightly soft material, this porosity can be minimized due to the load of top layers. Or else we have another solutions, like you can shift to some square or rectangular nozzle where you have minimum pores. Okay, so with this material data process parameter information, we tried to do some project. Our first project was to do some 3D printing of toilet units, which is around like 2 meter tall. So but during printing we found very interesting story that the design is also very important in concrete printing. As you can see in this toilet unit design, we have a curvature and it has different radius. So initially the radius of curvature was around 40 mm, and when we printed we found some crack. You can see the periphery of the material is having some cracks. So to avoid that, we started increasing the radius of curvature, and with more radius of curvature, the crack disappeared. So it means the design, material, and how fast you can travel during this turn, it all affects the material quality. So then we conducted some material testing to know what is our compressive strength, other mechanical properties. We found that like other processes, 3D printing part are having anisotropic property. They have different properties in different directions. But for the material that we have developed and our printing process, we didn't find much difference in three mutual perpendicular direction. As you can see from the graph, the strength in all the mutual directions are almost similar with a very slight deviation. So the material was more compacted in the X direction, that is in the printed direction. And one interesting point, we found that when you are conducting 3-point bending strength, the loading and the printing layer direction is very important, because we are more interested in F1 direction when the loading is directly in perpendicular to the printing direction. So what happens here, the bond strength of the material, it has a highest role, because the bond strength determines what is the strength that you are going to get from this 3-point bending strength. And then we conducted some bond strength study and with different time interval, and we found that with more time gap, as reported in many research by many researcher, the bond strength decreases. But again, it depends upon many factors, like how fast your material set, how fast you are printing, what is the time gap. Many factors are responsible that can affect the bond strength in concrete printing process. So we found that during concrete printing, if you slightly press the layers before you deposit the next layer, it sometimes it minimizes the cavity that happens in between these two layers. So it is not a guidelines, but again it happens with only soft material, because we have tried the same experiment with stiff material. This porosity never it's always there in this between the two layers. So then with this research, we have done some projects like 3D printing of tall structures like toilet unit. So our Indian Prime Minister, he visited our campus to inaugurate this 3D printed toilet unit. And then with a robotic arm, we have printed 3-meter tall bathroom unit. So as you can see, only the structure was printed, but the tiles, the foundation was casted. So this is the entire 3D printed bathroom unit that has been done using the 6-axis robotic arm, which you can see on the behind of the screen. So the complete video is here. Hope you can see it. Let me play it one more time. Yeah. Yeah, so then we did some research on the reinforcement for 3D printing concrete application. So as you can see, there are different methodology to reinforcement, but I don't want to put all this presentation at this time. But there are a few different methods that has been done in the research, which can improve significantly the ductility property of the 3D printed concrete. So, and you can see that we have also developed some facility for core bed 3D printing. So it means they can deposit the material on the core bed. And there are some experiment that has been done to print the entire structures with multiple robots. So there are different research group working in our team who they are completely focusing on developing new materials for 3D printing application using recycled glass. So they are optimizing the mixed design with respect to different particle size. And there are few projects that I have in my slides. I hope all of you are very well known about these works by Extreme Basics, Saibi. They are very popular companies, industries. They are doing a great work for concrete printing applications. Vincent, BAM Infra, and Eindhoven University. They are doing a very good research in concrete printing. Many projects has been done from their sites. So I hope with this pace of concrete printing, the key takeaways that I can present in my presentation, the texturotropy is important property for concrete printing application. And when you are developing the material, we should not forget the machine processing parameter and the design of a structure, which are very important. And all the three parameters are interrelated. And there are a few issues that is still need to have more research, like enforcement. There are some methods for testing is not evolved for different varieties of material that has been used in 3D printing. And of course, the last point, which is very important, that when you're printing a structure, how can we afford it? So the economic analysis is still under research. We need to find many potential ways to further bring down the cost. So this graph I have found from a paper that has been published in Cement and Concrete Research Journal. As you can see that at this time, at this moment, the digital fabrication, you have to pay more cost for printing. But the complexity, if it is increases, then the cost can be trade up. So hope with our in future we can do some research and development in this direction, and this curve can be minimized so that some structures which can be printed with a very affordable prices. So with that, I am concluding my presentation. If you have any question, please free to ask me. Thank you very much.
Luisa, you have to turn on the mic.
Thank you very much for your interesting presentation. I don't know if we have questions.
I have one question.
Okay.
Yeah, please.
Oh, okay. Thank you. So you referred the use of accelerators for tailoring the properties of materials for extrusion-based 3D printing. I was wondering if you tested some accelerators for geopolymer cement for that case.
Yeah, a very interesting question. Actually, I have a very good answer for this question. So when I started geopolymer 3D printing, my professor at NTU Singapore, he asked me why you want to print geopolymer. So before that, I was trying different geopolymer mix, and I found the mix design that I developed in my PhD. It is having setting time of almost like 15 to 20 minutes. So I found the material is rapid hardening nature by itself. So I don't need to add any accelerator. And then I proposed this material to my professor, saying that, Prof, this material is a rapid hardening nature, and just by controlling the concentration of the activator, we can make it rapid hardening. So it can be a good initiative if we can use this material for concrete printing, because we don't have to pay the extra money for accelerator. So for geopolymer, that's why I didn't use any accelerator. Rather, I optimized the setting time using the activator that I have used for formulating geopolymer.
Okay, thank you.
I also have a question. I'm wondering if you have tested the behavior of these materials to seismic effects.
Yeah, exactly. That work we have not done so far, but some research group we are trying to explore this kind of material properties. But our work was more focused on material development by modifying the fresh properties. So of course, some structural testing teams are working in this direction, and but I'm not expert in that direction. Thank you very much.
Okay. I don't know if you have more questions.
I have another one, if I may ask. Please.
Yeah, please do.
You referred also the use of pressing the layers during printing.
Yeah.
How do you do that?
So what you can do, like during printing, no, like normally we set the layer thickness, which is almost equal to the nozzle diameter.
Mm-hmm.
So normally, suppose having it 20 mm and set the layer height 20 mm. But we don't do that. We always put like slightly less than that, around 18 and sometimes 15 mm, so that the layer should be slightly pressed. And the effect that I have shown in my presentation, it only happens if you're using soft material. But if you're trying the same experiment with a very stiff material, the chances of minimizing pores are very less. That's what we have found from our experiments.
Okay. So we lost for some time the connection, and we couldn't hear you very much. But what I understood is that you adjust the layer height a little bit less than the nozzle aperture. Is that correct?
Yes.
Okay.
Yes, correct.
Okay. Thank you very much.
Yeah, no problem.
So no more questions. Florino, you have a question?
Yes.
For I don't know if you want to put.
Maybe if to keep in time, maybe I will ask him in another occasion because we reached the time. I want to thank Viranci. It was a little bit. Well, we lost the connection, but I think it was a nice presentation. We can see you, but I hope you are. I hope everyone that knows you can have your contact. Anyone that want to contact you, I'm sure that are able to contact you. And I want to
thank you very much for the invitation. I think you are doing a great work by this research community. This is a very interactive session, though I could not attend some of the lectures, but it is really interesting. My PhD students are attending, and I hope in future we can have some collaborations and we can do some joint research. Thank you very much.
Yes, yes, we will for sure. Thank you very much.
Thank you.
So we reach
Thanks.
the end of the morning session, Luisa. Yeah.
So we have now a break for more or less 1 hour, and the session in the afternoon starts at 13 13 and 30, I think. Yes.
Yes, 30. Yeah.
Yes, half
Yes,
past.
yes.
So I want to thank you all the speakers and also the people that have attended this section, that I think it was very useful. We don't have more questions, so I think that we finished this section. This is the morning, the section during this morning. That I think it was a very profitable webinar for all. And I don't know if you want to say something about it, Florindo, but for me.
Yes, we will continue at 1:30 set Central European Time, and I see you then. Thank you very much.
Thank you.
Thank you.
See you.
é meio e meia. Acho que sim.
Ok.
Ok, então, deixa eu ver aqui. Good afternoon to everyone. We'll start after lunch. I hope that everyone have a good lunch. And we will start now for the afternoon session that we have here 3 presentations. The first one came from Sandra Lucas, that is about sustainability and functionality and additive manufacturing. Second one after will be given by Alban Mallet from X3, also 3D printing in construction. And the last one, it will be given by Florino Gaspar, regarding materials and digital building. So I will say some few words about Sandra Lucas that will start the afternoon session from Eindhoven University of Technology. And let's see, okay, Sandra is an assistant professor in 3D concrete printing in the Department of Built Environment of University of, Eindhoven University. And in Netherlands, Dr. Lucas is an assistant professor in 3D concrete printing with the research group Concrete Structures at the Department of Built Environment in the Netherlands since 2018. Her research focus on developing fully customizable 3D printing materials on buildings. Dr. Lucas obtained a Bachelor Engineering in Ceramics and Glass Engineering and a Master in Environmental Management and Materials, and in 2011 a PhD in Civil Engineering from the University of Aveiro, Portugal. She then became Marie Curie postdoctoral research at Fraunhofer Institute at Oberhausen, Germany, for the CheMate project. As part of this project, she was a visiting research at ESI Paris Tech and Delft University of Technology. In 2014, she joined the University of Greenwich in London, UK, as a senior lecturer in construction materials and sustainability. She is a project leader of 2 NWO projects to develop smart and sustainable 3D printing construction materials. And she will talk about sustainability and functionality, new challenges for additive manufacturing in construction. So please go ahead, Dr. Lucas.
Hi, good afternoon. So I'm going to start by sharing my screen. I hope it will work. So I'm just going to put it on slideshow first, and hopefully I will be able to share it. Okay, just bear with me one moment, because I think my slide share is moving too fast. I'm just going to try and go back. Can you see my screen?
Yes.
Okay, but I was supposed to be able to go back, and I'm not. Okay, that's not supposed to. Okay, so now it started. Okay, so thank you very much for the invitation, and it's a pleasure to be here today. And well, the introduction has been made, so I'm just going to switch to the presentation. So I'm going to talk about sustainability and functionality, and these are new challenges for additive manufacturing. And there's been some research now in the topic, but I think there's still a lot to do in that field. And I'm going to briefly explain why. So first of all, with 3D concrete printing, the main goal here is to meet industry needs and industry standards. So the focus of research since the very beginning is to make this solution commercial. But of course, there are some concerns in construction right now, and this is especially important in the Netherlands and also in Portugal and in European Union. These are the environmental concerns related with the industry, and not just during the construction phase, but also during the building life cycle. And we all know about the statistics that 30% of the total waste produced in European Union is generated by the construction industry. And there's a lot of issues that need to be tackled regarding the extraction of materials, raw materials, energy consumption in the construction sector. And this was also one of the main drivers to try to create new solutions for the construction industry and the manufacturing of buildings. The other concern is with automation, because the construction sector is one that only the agricultural sector spends less money than construction industry in automation. And automation is not just 3D printing. It concerns, so it's much more, much broader than that. But the truth is that we still spend very little money on this topic. And if we compare to other industries, like aerospace and biomedical, they do spend a lot more, and they are much more advanced in this field than the construction sector. And of course, okay, it's getting a little bit, so I'm going to just use this one. And of course, there's also the topic of innovation, because the building sector is not much innovative. We are still using basically the same materials that we have been using for centuries, some of them, and some of them for the last century, they haven't changed much. And I especially like this picture because it shows a building that when it was built, and at that time, it was also quite innovative. This is a building by Le Corbusier. It's his home in Paris. And this is an example that we need to innovate again. We need to move forward. And the innovation in the construction sector, in my opinion at least, also needs to come from adding value to the buildings and adding value to the materials. And this can come from, for example, adding new functionalities to the buildings and making buildings smarter, and also building in a smarter way, I think. And then we have the issue of safety. And this is also very important because the construction sector is also one of the sectors where we still have a very high level of accidents and deaths in construction. It's not a very safe industry if we compare with other ones. And this is directly connected with the lack of automation, of course, because there's still a lot of dependency on human labor in the sector, and we need to change this. And some other factors that are drivers for innovation in this industry are also related with the housing costs, and this is something that is also becoming a very important topic in Portugal and also in the Netherlands. In the Netherlands, we have a housing shortage that is quite significant and also very expensive. So we need to create an industry that is lower cost, that is low cost. And we also need to deal with the regulations, because this is also an obstacle that we experience when working in additive manufacturing in construction. We felt that when we developed the bridges, and I was involved in the development of the Nijmegen bridge, and we noticed that the difficulties to prove that these solutions and these materials are suitable in light of the current regulations, and especially the Eurocode. So this needs also to be updated, and we need to find ways of changing the obstacles that are in standards and regulations. So the ultimate goal that we have, and of course we do research at TUE, but we do research with a focus on making the solution in the end, and this is our goal, to make it commercially viable. So we want to upscale, and we want that one day buildings will be available for anyone to buy them and to print them. And we need to find a way to get there. So how to get there? That's the main question right now. And one of the biggest issues, or one of the biggest part of the research that we do with 3D printing relates with materials. And this is my field of research. So I'm focused on the materials side of the research. And the first goal in 3D concrete printing was to make the materials fit for purpose. And in order to make them fit for purpose, so we have this ink in 3D printing, and we can call the concrete the ink in our field. We call it concrete, but of course we are still at the mortar level, and this is also a discussion. And this is also a problem right now because we don't really have a concrete. We don't really print concrete. We print mortars because the size of the aggregates is quite small, and we don't use yet coarse aggregates in the mix. So this comes with some issues that I'm going to discuss about. And one of the biggest one is the high amount of cement that some of these compositions still have. So there's a complex cycle of to develop a mortar, to develop ink for 3D printing, for printing buildings, and this comes firstly from the mix design. So the mix design is the one of the most important parts of developing a 3D concrete that is suitable for printing. And we start, and this is also something that already my colleague, Professor Panda already discussed this in the morning. And first of all, we need flowability. So we need a material that is flowable enough to be pumped and to go through the holes of the equipment. So in the very beginning, we need to make the material flowable. But at the same time, we need to make this material extrudable. So it needs to be extruded and it needs to be pushed through holes, and it needs to reach the nozzle in conditions to be extruded. But then we also have the issue of buildability, and this is also a hot topic of research, and I don't work directly with this part. I work with buildability up to the mix design, but there's a colleague in my group that works with the buildability part and the simulations to understand how high can we print, how long can we print. And the buildability is also the assessment of how can we print the material without causing the material to collapse. And of course, this is fundamental in 3D printing. And we also have the issue of the open time. And in the morning, we have seen the presentation about geopolymers. And this is also very tricky and especially difficult with geopolymers. It's harder than with a standard cement mortar because the open times sometimes tend to become shorter with geopolymers. So with materials, if we want to make the material more sustainable, we also need to take into account the time that the material is suitable for being pumped, extruded, and built as a wall, because we also don't want the material to clog in the system, because that will be an absolute disaster. And we have, in the beginning, we experienced that sometimes, that we had some materials clogging the system. And this is very time consuming, and it can, in the end, if it's really extreme, it can completely compromise the equipment. So all these topics, all the flowability, the extrudability, these properties, they are directly related with the rheology of the material. So the viscosity, the way the material flows, and the way the material behaves. And we adjust the rheology of the material to fit these criteria that we need for printing by using superplasticizers, by using retarders, by using accelerators, viscosity modifiers. One of the problems that we encounter now is that most of these additives, most of these admixtures that are used with 3D printed concrete, they have not been developed specifically for 3D concrete printing. They were already in the market, and they were used with self-leveling concrete, with standard concrete that we poured into a mold. So we also feel they're not ideal. And this is a side of the research that we don't do in our group, but we feel that we sense this need, that we need the companies that develop these additives to also keep up with the research that is being done in the 3D concrete printing and came up with solutions. But at the moment, we don't have them. So we need to deal with what we have available in the market, and what we have available in the market are the old additives that were used in standard concrete. And so for now, we work very much with these ones. And sometimes we also use experimental ones or new ones, but it's mostly the standard ones. And of course, in the end, we also are concerned about the hardened properties and how the material will behave after being printed. This concerns with durability of 3D printed buildings and the tensile properties, because in most of these materials, we don't have what we call the reinforcement in a traditional way. So we don't have the steel rebars, they're not there. And we use fibers, sometimes steel fibers, PVA fibers, polypropylene fibers to try to improve the tensile properties. We also combine the rebars sometimes in a creative way with the 3D printing, but there's no ideal solution for now. So we need to come up with a material that compensates for that compensates for the lack of reinforcement. This is also a challenge in the 3D printing. So in the end, this is a full cycle that needs to be met. And some of these requirements, they can be contradictory. The extrudability contradicts the flowability. So I want a material that is flowable, but then I want a material that when comes through the nozzle, needs to be buildable and needs to stay and retain its own shape because I don't have a mold. So some of these requirements are contradictory, and some of these requirements, they also compromise the hardened materials in the end. So we need to come up with solutions that keep the material to a very high standard and to keep the material to a level that meets the requirements for example, the Euro codes. But at the same time, we need to make the material workable for 3D printing. And all these challenges, they also come up with an extra problem, because we need to meet also the goals for the Industry 4.0. So it's not just about making standard materials, because I don't think it is interesting to use a technology that like 3D concrete printing to make the exact same materials that we have been doing for a long time. So it doesn't make sense to create a standard mortar and use all this process to do it. So there are other needs now that need to be met. And one of the most important one concerns with sustainability. Because first of all, we need to lower the cement content. And for example, in the Netherlands, we have now the Beton Accord, which is the concrete agreement, that's the translation, where the companies in the Netherlands, together with the government and together with the researchers, they signed an agreement with the goal of removing or reducing considerably the amount of cement that is being used in construction. And this is, of course, because of the high CO2 emissions coming from cement production, because we need to reduce the carbon footprint of buildings. We also need to reduce the energy demand. We want to make the buildings zero energy, and ideally by 2030. Now the goal was before 2020, but it has not been met. And we also need to design for circularity. And sometimes this is also, these requirements are also contradictory, because some solutions that we develop, then they don't work very well in a circular building from the circular perspective. So we need to look into these new topics of sustainability, and we need to take a step further. We develop inks and we develop mortars that work with the 3D printing. That's a reality. We already have at TUE several of our own recipes that we can work with. But what we have to do now is to look into how sustainable these materials are and how can we make them more sustainable. And on the other side, we also need to come up with solutions that are helping to make the building zero energy. So that's why I came up with one of the projects that I have now is precisely in additive manufacturing of sustainable concrete for zero energy buildings. And what I'm going to show you here today is also a brief summary of what we already have done in these projects and what we plan to do next. And in this first project, this is a project funded by NWO. So NWO is the Research Council for the Netherlands. So it's the same as, for example, FCT, Fundação para a Ciência e Tecnologia in Portugal, or the Research Council in the UK. And together with a group of companies from the construction sector, manufacturing of materials, Weber, and certification, SGS, we are trying to develop more sustainable solutions for 3D printing. And one of the solutions that we developed so far is precisely geopolymers. But in this specific case, we developed not a full 100% geopolymer, we developed hybrid mix. And we used iron-rich slag because this is a material that is available in the Netherlands and in Belgium. So in the Benelux area, it's quite abundant, and we have it, and it is available. It's a waste, and it is a fine way of reusing this waste and to give it value again. So we replace cement with this slag, this iron-rich slag, and we use it as an alternative binder. And we got with this research that is still in its infancy, so it's still in the very beginning, but we already managed to see very, very interesting results. And you can see here some of the samples that we printed so far. And the interesting thing is that we managed to print higher in some situations than with a commercial product, with a 3D printed concrete that is available commercially, and it's based cement based. These are hybrid mixes. So to make it clear, this is not 100% geopolymer. We still use a very small amount, 16% of cement in the mix. We believe we can reduce it up to 10%, maybe even less. But we still need a little bit of cement. And this is directly related with the conditions to prepare geopolymers, because we need an alkaline environment. We need high molarities to activate the binder. And to work with 3D printing, this is not ideal because we're using materials and we're using an equipment that is very sensitive to alkaline corrosion. So we need to be careful, and we need to keep the molarity at a lower level. So in order to get there, we use a little bit of cement in the mix, and this helped a lot also with the workability of the material. The results were very, very interesting, and we found out that one of the things that we found out is that we have a lower shrinkage and creep with a material, a hybrid material like this, compared with the benchmark material that we tested, so the commercial material. We also found out that some additives like silica fume, for example, can contribute to a better early age buildup, which is quite good because we're able to print higher if we include silica fume in the composition. So this was a really interesting work that we already have a publication that was submitted during the second RILAM conference. It was presented there. We are now finalizing 2 new papers that should be available soon. This is also a collaboration that was together with Glenn Beerserts, a PhD student from KU Leuven that finished his PhD very recently. And we are preparing now these 2 papers in the topic, so they should be available soon with all the results that came up of this research. But of course, the development of sustainable mixes is not just about the mix itself or the finding alternative binders. Now we plan to look into other alternative binders that we can use. We're looking to, currently we're looking into using volcanic ash, which is also quite abundant still, not as fly ash, because fly ash is really disappearing from the Netherlands. Last time we tried to order fly ash in the Netherlands, we struggled quite a lot to get it, and we had to order it from outside the European Union. But there's still some availability of volcanic ash in Europe, that also an interesting material that we want to test. And we are also looking into ways of tackling the problem of reinforcement, because it's not just about making the material more sustainable. We also need to keep the material with a good level of tensile properties. So we need to keep up with the tensile properties. But ideally, we should also think about solutions for the reinforcement that do not go through using steel fibers or steel rebars in the material. One of the studies we did recently, and we just there's a master student that just finished this research, was the use of natural fibers in 3D printing. And in this first study, we selected hemp fibers because they're also available and there's also quite abundant. Of course, they're not locally available in the Netherlands. So now we're thinking about using and exploring the use of other fibers. But the interesting thing is that we found out with some of the first results, and you can see here the printing trial that we did with the mix. You don't see the fibers here, but they're there. You cannot see in the material, but they're mixed in the material. They're quite well mixed. They're quite small. And the reinforcement showed a comparable performance to the polypropylene fibers that we have used before. So we're not losing properties by using hemp fiber mix in the material. And we did small scale print trials that were successful, but we are now looking into preparing a bigger print trial. So we're going to move from the robot arm to the printer that we have at TUI, the big one. And we're going to see how that goes. And we are also looking into using other fibers in replacement of hemp. But this is a topic that it's quite new. I'm not aware of anyone else. I think there's a group in France that is also trying to do some research with natural fibers for reinforcement of 3D concrete printed. But this is pretty much what I know so far from natural fibers. So this is quite new, but I think it's a very interesting topic and with a lot of potential and a lot to know and to learn about. And of course, not just about sustainability, but as I mentioned before, we also need to look into the innovation in these materials and look into adding value, especially with new functionalities. We need to add value to the materials because we also need to make the users of the buildings to understand, okay, they're using this sophisticated technique, this 3D printing to print a house, and then it's just a standard material. And not just a sustainable material, but we also want to make it a material that can add something to the building. And we're looking into adding new functionalities to the building. Because in materials with functional materials for construction, they're not new. They have been developed for many, many years now. I did my PhD, I started my PhD in 2008, and I work with functional mortars for construction. So this is not new, but they're not being transferred. This knowledge so far has not been transferred to the 3D printing systems. And this is because people are focusing still a lot in making the material work. But we need, I feel that we need to move to that part now to create smart materials. So this is the second project also funded from NWO, and this is a bigger consortium, so a consortium of 7 industrial partners, and that includes NanoSeal, a manufacturer here in the Netherlands for carbon nanotubes. And we are trying to look into additive manufacturing of functional construction materials, and we want to do it on demand, and I'm going to explain what on demand means in this specific case. So when we look into the solutions that we already have there, like for example, self-sensing 3D printed concrete, this is not new. So people have already researched about adding carbon nanotubes and graphene to cement mortars. And they do it to improve the tensile properties and to create an extra functionality in the material, which is the self-sensing. The self-sensing, it's a way of using the carbon nanotubes because they're conductive in a way that we can use them to detect, for example, defects or cracks in the material. I feel this is a very interesting solution that we can use in 3D printed buildings, because again, the safety concerns came up every time we discuss 3D printing with the construction sector. And if we're able to detect cracks and we're able to detect where they are and repair them, we can make buildings safer, more durable, and we can save a lot of money on unnecessary maintenance activities that we sometimes we don't need to do them because it's still too soon, or avoid doing them too late. So this is a research that we're doing now, and we already have some results. And of course, this comes with challenges, especially when we work with nanomaterials. Nanomaterials are very difficult to work with when you work with a standard concrete material or a cement mortar, but they're especially critical when you work with 3D printed materials, because not only you need to find the right composition to include the carbon nanotubes, but you also need to make the material suitable for 3D printing. And this is really hard to achieve. And one of the biggest, the first issue that we encountered was just with the mixing process. So just to develop the mixing process for these type of materials, it's already a full research on its own. So we are in the stage of, optimizing the mixing process, which I believe that we optimize already. So we got there very recently, and now we need to study the rheology, and we need to find the right adjustments to make the material printable. We were already able to print the material in a very small scale. So we already have a printable composition that includes carbon nanotubes. We need to also to do more research into the printability, the durability of these materials, and also the shrinkage and creep. This is very critical with these materials, because sometimes we need to increase the amount of superplasticizer. We need to compensate in some situations with a little bit more water. So shrinkage and creep are a concern with carbon nanotubes and graphene nanoplatelets. And we also need to do research on the conductivity. So can we indeed see the conductivity or changes in conductivity in these materials if they are cracked, if they have cracks, if they have defects? So this is something that we are now going to, we plan to start this part of research in September. We already have an equipment that we ordered to measure the resistivity of the material. So we're going to move to that stage at this level. But there's a lot of challenges that we need to still overcome with this research. The other part of the research that we're doing, and this is a collaboration with TU Delft, and I work together with Professor, yes?
Sorry, I have some more 3-4 minutes.
Okay. I will try to be fast.
But it's interesting. I'm enjoying your presentation very much. Okay, very interesting. Okay, continue, please.
Okay, I will be super fast in this part. So we are also working with self-filling 3D concrete printing, and this is a collaboration with Professor Henk Jonkers from TU Delft. We're using now bacteria to create self-filling and to try to transfer the knowledge they have at TU Delft from self-filling materials to the 3D printing solutions that we have at UE. And this is very, very interesting, but we are facing a lot of issues with this material in particular, but it's really interesting and it's quite challenging, but we are very, very positive that we're going to have also results very soon in this topic. And hopefully in the end, we hope to combine both. So the self-sensing and the self-feeling in just one product. And of course, all these solutions, all these new innovative functionalities, they don't fit the printing systems that we have right now. And this is also a part of this second NWO project. We want to develop a smart printing system. And right now we are rethinking the whole printing system that we have at UE because we want to be able to print on demand. And this means I want to print a wall with self-filling and then I want to switch to another part of the building, for example, for self-cleaning or for self-sensing. Then I want to do it without having to stop the printing and restarting again with another material. But in order to achieve this, we need to rethink the whole system. And this is also something that we are doing right now. And we are still working in the theoretical part, so we don't have a solution yet. So this is a PhD research from one of my students, and we hope to have one by the end of the project. So of course, I couldn't finish my presentation without saying that this is not my work alone. So this is a joint effort of several researchers, PhD students that are working very hard to get there. And you can see their names and their faces here because I wanted to show you that there's all the people that are working behind all these solutions that I showed to you today. We expect to have another two one PDeng and one PhD student joining us this year, and then the group will be complete for now with for these two NWO projects. So thank you very much for the invitation. Thank you very much. I hope you have enjoyed, and now I'm open to questions. You can also see here my email address if you want to contact me after the seminar. Thank you.
Thank you, Sandra, for your excellent and very interesting presentation. And now I ask you, the audience, to ask some questions to Sandra.
I think I have one. Can I make one question?
Yes, please.
It was very interesting presentation. I was curious about some of the subjects you presented, of course. And for instance, I would like to ask you about the carbon nanotubes. Was it easy to insert the carbon nanotubes in the mixes?
No, not at all. It's something that we're still working with. We tried different ways. We haven't tried the sonication yet, which is the most common one. And there's a reason for that, because we want to avoid doing that, because sonication, although we feel that might be possible to add to the printing system, is something that we want to avoid. So we're trying combinations of super plasticizers and high-speed mixing to be able to mix the carbon nanotubes. That's not easy, but we managed to find a solution right now that, well, it's a combination of, as I said, the high-speed mixing and the right order of adding the materials, because that's quite important. So the carbon nanotubes, from our experience, should be added first. They come as an emulsion, so we're not using them as a powder. Also for safety issues, because coming as a powder, you need to have a certain conditions in your lab to be able to handle them. Although they're not a nanomaterial per se, when you handle them, they come as aggregates of materials, so it's a micro-sized material. And we're using multi-wall carbon nanotubes. but I can tell you that in the beginning it wasn't easy. Now that we know the process, yes, but it's a challenge. Yes, you're right.
Thank you.
More questions? I have one question regarding the fibers that you are using, the natural fibers. The natural fibers that you are using are short fibers. What is the length of each fiber?
I don't recall exactly the length. I have to go back to. I have to check the paper, the paper and the research that my student did so far, Naomi. But I can tell you that if you send me an email, then I can send you the exact length. But they're relatively short. Yes, they're short, because if you use the bigger ones, then they entangle. They are difficult to disperse. So we kept it on the shorter side. I can do a quick check now, and even I can answer you via chat, but quite frankly, now I don't recall the exact length.
No problem. Thank you. Thank you very much,
No problem.
Sandra. There are more questions? So if not, thank you very much again, Sandra, for your excellent, very interesting presentation.
Thank you.
I hope in the future to buy one of these houses that you have behind you. Thank you very much, and we move to the next presentation. Thank you very much.
This is the first one, and I think it's still open. So if you want to rent it for a short period of time, I think you can still do it.
But it's expensive, perhaps not? No.
Quite frankly, I have no idea about the prices. I know they have tenants now, and I think these tenants will be there for 6 months,
Okay.
and then they have to move. But yeah, we're going to build another 4, so you still have time.
Okay, thank you very much. Thank you very much.
Micro.
Okay, okay, sorry. Now we are a little bit delayed, and we move to the next presentation that comes from Alan Mallet from X3, Industrialization of 3D Printing in Construction, a new process from design to production. I will only give some words about Alan. And okay, Alan Mallet is a CEO, architect, and co-founder of X3. He's an architect graduate of ENSA Paris Malaquais in 2015. He was been working for several years on additive manufacturing processes and biosource materials. CEO at X3, he is in charge of development of 3D printing capabilities of the company, and in the conception of new technical and strategic means of large-scale 3D printing. Please, Alan, you could start your presentation.
Hello, everyone. Can you hear me?
Yes, we are hearing you very well.
Perfect. Just try to make the slideshow. Is it in full screen and is it working? The slideshow?
Yes, it's working.
Yep.
Okay, perfect. Thank you very much for the invitation. Thank you for all the great presentations. It was really interesting, and to see all the development of 3D printing over the world. So my presentation will be to explain how we start from prototyping to have industrial grade solution for 3D printing in construction, and how we see the production of 3D printing from design to production, and how we are working, what's our model, economic model, and also what is our aim. So that's really important to see our vision. So it's to shape a desirable and low carbon built environment. So that's really our aim in the company. As mentioned, we are architects from training, and that makes us really aware and concerned about how we build today and how we can manage to do something better and greater. As you mostly know, what's the problem in construction, the productivity, the waste, and the time and cost during construction projects. Answer to those problems are lower material consumption using 3D printing, so we can manage to have complex shapes where you optimize the quantity of material and you just put the right material at the right place. We do lighter structure, faster construction, we lower the cost, and they are all tailor-made designs. So all the designs are made not just because it's efficient for production, but it's efficient for the final building. So that's why it's really important to make tailor-made design, and that's why what these tools of 3D printing make us able to do. Our mission at X3, so we are concentrate on construction, but in prefab. So we are not going on site, but we do off-site 3D printing. And we are trying to make a network of 3D printing facilities all over the world, where you're gonna have our system attached, and we're gonna help constructor and precaster to have our technology and to be able to print interesting products for their clients. So today we have 2 facilities in Paris, 1 in Japan, 1 in Dubai, 1 in the United States, and we are continuing to push because we think we need to do local production to answer the local problems and not having shipped elements all over the world. Our technology is fully automated. So from design to production, we mix and we print directly from one flow of data and one flow of the concrete is flowing through from hard to wet to after to the printing. We'll do also multi-component 3D printing where we have patents on it. So the idea is here not to print. So there's 2 families of 3D printing. One where you mix your product is starting to set and you need to deposit it as fast as possible because you don't want it to set inside your pipe. And what we have made and learned during all our process is to develop this system where you have low setting material and you accelerate it inside our technology so you can manage to make it set on demand and you are not going to wait for the material to set by itself. So we control the workability and the setting time of the technology of the material. We'll also do multi-material. So we have worked and we have developed plaster 3D printing with Saint-Gobain. We have worked on clay 3D printing. We are working on geopolymer on a European project which is named Wool to Loop. And we also do multi-robot collaboration because we want to fully automatize from the start to the end of the process. So this is our technology. Basically, you have a 3D model where we manage to work with architects, civil engineers, and we adapt the shape regarding the needs of the project. When you are finalizing to design, this is automatically sent to the printer and you set your material, your pump, you send to the printer and the printer is going to print your elements. Also, we have made a lot of interfaces to have good vision over the quality of the print. And if you need to do some online modification, this is fully automated and you can manage also to make some adjustments during the print. Some view of our technology. And I wanted to show you, I think the best to show the technology is one of the video of our partner, which I've made a video to showcase what's possible to do. So this is the Kurabo, which is one of our partners in Japan. As I mentioned, we want to have partners all over the world to do local 3D printing and to answer local problems. This is our head, where you have the concrete, liquid concrete, which arrives. We control the quality of the concrete. And inside the head, we control the flow, we control the setting time, we control everything. Here you can see some of our software. So we are based on Rhino and Grasshopper. And on this software, we have made our own plugins where it's much more easier to print and to control the printing time and the speed of the robot, the quantity of the concrete, etc., etc. So inside our nozzle, we inject the accelerating agents. We mix it and we do on-demand setting. So we can go make like large pieces with long time between each layer, or we could do small pieces with like 10 seconds between each layer. And we managed to be sure that the quality is great like this. Also, we do a lot of data monitoring. That's something we learned from the start. We need to have all this data. One is to understand what's happening inside the printing head, but it's also to improve and to ensure the quality, because our idea at the end is to say, okay, at the end of the print, we are sure that the quality is here. So it will be relevant to have the certification over the product. Also, we control the geometry, the exact geometry which have been realized by the robot, also for certification and proof of quality. Here it's two things we have developed also. We have developed some software analysis. So we managed to analyze before we print if it's going to stand or not, and which type of parameter we will have to tune before the printing to ensure that it's going to stand. That's something we recently have developed, because before we were learning in printing fail and learning to see when it fails. We redo and fail, but this is not possible if you want to be in a reasonable, profitable industry where you industrialize your process. You don't want to have some failure. So that's why we have developed our software to analyze if it's going to stand or not. This is our business model. So we are going to create, and we have created a platform. This platform connects the precast industry with our technology, designer, constructor, end user. And so we are here to create an ecosystem around this tool. We are not just here to make it able to print, but it's more a question of how we're going to print, what we're going to do. And with this platform, we can connect all the ecosystem to think of better solutions. I'm going to show you some projects we have done just to showcase what's possible to do and how we achieve to go at an industrial grade, where you go from prototyping to real industrialization of 3D printing. So this is one of our first projects where we have printed a casting mold, where we have put some UHPC inside. So the calculation and the certification have been made on the UHPC which have been poured. And that was an old project that was 4 or 5 years ago, where we were not able to certify the 3D printing concrete. But as I mentioned, all our aim is to reduce the footprint. So we need to put in calculation every element of concrete which have been used, so we can reduce as maximum of the CO2 footprint. We have done another project quite recently, which we have finished with Plurial Novalia, which was the client, and we managed to print parts of a house which have been designed by Cost Architecture. And in this project, we say that there is no sense to 3D print all of the house, because there is standard elements in a house. And if you want to lower the cost, there is an industry for precast with really cheap elements where the costs are really, really low. But what we wanted to do is to have 3D printing to have more value to the house and to adapt some shapes from the needs of the architect or for the constructor. So we work with them and we explain what's possible to do and what it will be relevant, where it will be relevant to put 3D printing. So that's how we design it. Also for this building, we have been 2 years going through certification in France, and we managed to have the concrete, the 3D printing concrete into the calculation of the building. So it's not just the casting mold where it's not taking in account, but it is used in the calculation and for the reinforcement of the building. So this is some interior views, and that's how it has been put inside, on site. For us, precasting is really interesting because you can manage really to reduce the time and process on the working area. So the only thing you need to do is really to think about how you're going to assemble them. But when you start to think about that, we have an industry of construction which is quite well developed to know how we're going to assemble and we're going to build like a Lego hold the elements really fast. And so we're gonna reduce the cost and the risk on site of the construction site. So these are some pictures. Also, I wanted to showcase some other projects where maybe you can't see at first where is the value of 3D printing. Here is a stormwater collector, which have been made like 3 years ago, I think, in Lille, in the north of France. So the problem for stormwater collector is when we need to do like adapted stormwater collector or other underground stuff. Most of the time, classic elements, standard elements don't fit to the need. So what they have done since many years is to put some wood and to pour concrete, but this is quite dangerous, not effective, and not good quality. And so that's why we have developed this project where we have opened the road, we have scanned to see what the shapes we need to do. We have 3D printed on our facility and ship it and to install. So that was reducing the time of and the precision and the quality of the stormwater was quite better and that. We also have done some excavating masks for the starting of the tunnel excavation tunnel. We have worked also a lot on civil marine engineers for artificial reefs, where when we looked at what the solutions that already exist, most of them are not adapted, and you can make a parallel between humans and fishes. We tried to do houses for fishes like artificial reefs before, but they were not adapted. We used some wheels, we used some other stuff like to create, but it was not adapted. So we have worked with civil marine engineers, and they design all the pockets to be adapted to all kinds of species. So they could be little fishes, they could be like squids, etc., etc. And this is creating a biodiversity. Also, that was quite interesting because it was not just a prototype, but it was 40 elements which we have printed. So we have to be sure of the repeatability of our process. And it's not like when you do a prototype, when it's not working, you do another one. But we had to be sure of our process and to be sure that the repeatability was good, because we need to be profitable on this project. This is a little video showcasing how it's working. So as you see, the printer is moving. We deposit layer by layer concrete, and we managed to adapt each shape for the different type of fishes. Also, it was quite great because we had algae quite fast arriving on the elements, because we managed to look at to be sure that the pH of the concrete was great for the algae, etc., etc. And that was quite a good solution. I think we tried to manage, and we continue to have a lot of projects like this, and continue to work and see how far we can go on those marine fishes environment. So, yeah. So fishes. Also, we work a lot on infrastructure. This is a 12-meter telecommunication tower. And that was quite interesting because we didn't want just to 3D print by itself, because we know that 3D printing by itself is not enough for construction. So we have worked a lot with the Freycinet, and we worked on pre-stressed elements to manage to be great against the wind, against the earthquake, against everything. And also, it's not an ugly building. So the aim here is to have a great integration inside any type of landscape, etc. And as I said, we try to make it better, but also more eco-friendly, but more beautiful to be adapted to the site, etc. Also, this is a little picture video. So it was 6 elements, which have been placed on top of each other, and after we have pre-stressed inside the tube you see in red. So as you see, this is a robot working in our facility. And we were making between 1 or 2 elements per day. So as you see, it's quite a fast process. And after, they assemble it on site. So as mentioned, it's really important to see how we can collaborate with traditional construction. And the in-between for us is really where it's relevant to use the 3D printing. We also do some furniture, and that's funny when you think that we are doing under road structure, but also making furniture. But for us, it makes sense because if you manage to have high quality furniture, you ensure that you have good control over your system. The only thing is to be sure that your system is not too expensive when you are using it for under roads or for furniture, because furniture are quite selling at higher price. But for us, what was interesting is really to be able to, if we manage to do good quality furniture, we can do really, really great control over process for construction. And we need to push the same effort as we put it in furniture. I want to mention this project. This is a project we have done for Roche-Beaubois, which is a fine constructor of furniture. And we developed with them a process where you can manage online to modify the shape of the table. And that's something we are working on, but not just for furniture, but working on this for all the construction industry. Because as I said, we are not working just on the 3D printer, but we are working on a process where you go from design to production. And if you want to have someone using and adapt their design, they have to use simple tools. So this is a really great solution. And today, people are going online, they change the parameter, and after we receive just the data, we put it in the machinery, and we manage to print all the elements, and all the elements could be completely different because we are sure it's going to be printed. So we adapt to the needs of the different people. Here you can see a small video where you see the printing time and the quality of the print of the elements. So this is the final project I'm going to show you. This is a footbridge in the north of Paris, which is 40 meters long. And it's one of the aims of the project we are looking for, because in this project, all the concrete we are printing is part of the calculation, and all the concrete we are printing is the structure of the element. As you see on the right, we have made some topological optimization of the bridge to reduce maximum the quantity of material, and we create some alveoles inside. So it's hollow structure, and in this structure, we're going to do as we have done for the pillar. We are going to put some pre-stressed elements, and we are going to assemble them on site and pre-stress. So we managed to have something quite light, but really strong structure. To finish, when we speak about sustainability, I think the last presentation was really interesting because we need to work on the material. And that's something we have done here. We have put some light aggregates. So I'm not sure we can speak about aggregate, but we have made bigger elements, and we changed the formula to reduce the quantity of cement inside the formula to be able to reduce the CO2 footprint of the bridge. And it was quite interesting because we put some aggregate, but the resistance was the same because the ratio of cement was quite high. So we managed to fine-tune the formula to reduce its CO2 footprint. And we are continuing to push with other type of material, as I say, geopolymer, clay, plaster, because we think that every material has his place in construction. And the most important thing is to put the right material at the right place to be sure that we ensure great quality and to reduce the maximum the CO2 footprint we need to tackle. So that's it. I try to be as short as possible because there is a lot of information, But don't hesitate if you have some questions about the presentation, and if you have some questions, be pleased to answer them.
Thank you very much, Alban. And now we have the space for questions, if you have questions.
Can I ask a question?
Yes.
To Alban. Alban, I saw that I think it was a tower that you built in separate elements. I saw that you separated on parts of a certain height. That one. My question is, that height was because of some limit, I suppose, yeah. And that limit is related with the material, with the transport, or with anything else?
The problem of the height was because of the transport, first of all, because we need to have transportation not bigger than the regulation, because at the end it will be too expensive if you need to transport even for a few kilometers. If you have to have a convoy specific dedicated, that's too expensive. And also for manipulation, because if you have too big elements, it could be hard to manipulate them because they are too heavy. And we want to reduce also which type of crane you're going to use and to manipulate it. So that's why we have divided in 3 parts.
Okay, thank you.
We have here a question from Sven Bielan.
Sven Bielan, thank you, Penn State,
Okay,
in the US. So I had a question. You talked about using lots of different types of aggregates. What size aggregate are you able to use now through your process?
So now what we're going to use for the bridge is going to be between 3 and 4 millimeter aggregate. So not sure we can speak about aggregate, but at some point they make the same effect as larger aggregate. Just we're going to put a little bit more than larger ones. So that's how we manage to do it. Also, our aim is not to put aggregate. Our aim is to reduce the CO2 footprint. That's why we are not focusing on just putting large aggregates. And also what you need to look at is when you look at the size of the printed layers we are doing, we go from 2 millimeter to 15 millimeter high. So you can imagine if you have larger aggregates, that could be complex to print because you need to have cement all around the aggregate. And because we are focusing on also in high quality, precision, etc., larger aggregates will be maybe remain for when you need to pour like large elements, you're going to use large aggregates. But if you need to have fine design with small layers, that's where you use smaller aggregates.
Thank you.
Okay, thank you, Alban. There are more questions from the audience. So if not, thank you again, Alban, and we will move for the last presentation of the afternoon. Okay, thank you very much for your excellent job work. Okay. So let's move to the next speaker, that is Florindo. Florindo, you know very well Florindo. He started working this morning early, so he will finish this session and the webinar. He will talk about materials and processes for sustainable and digital building. I will say that Florino Gaspari have a PhD in civil engineering. He's professor at Polytechnic Institute of Leiria and researcher of CDRSP in Marinha Grande, also from the Polytechnic of Leiria. He made his PhD in civil engineering in the University of Lisbon. He is responsible in CDRSP for the Laboratory of Building Materials and is coordinator of the graduation and master degree programs in civil engineering. At the present, he is responsible for the Print Big Laboratory at CDRSP. He is the head research for the large-scale cement-based 3D printing group at Head Additive project. That is a project funded by the Portuguese Innovation Agency. His main research focus is related with innovative and sustainable materials and construction processes. He was involved in several technical consultancy studies and is co-author of more than 40 journal and conference papers, 8 book chapters, and co-editor of 2 books. He is involved in 9 research projects, 2 international and 2 as a principal investigator. So please, Florindo, go ahead and start the presentation.
Thanks, Sergio, for the long presentation. I think you can see my screen now, yeah?
Yes.
Okay. So, so my proposal here of this presentation is to make a wide overview, more or less wide overview about materials and building processes towards the sustainability and digital building. And I would like to start saying that this work was done by several people. They are in the slide below, in the below part of the slide. And these people who make these results that I will present, they make these results possible. So I belong to the CDRSP. The CDRSP is a research center located at Marinha Grande, Portugal. It is located in the industrial area and it has a close relation with the industry. We work with several companies and our work is mostly related, I can say maybe 90% related with the needs from the industry. Under the slogan "Manufacturing a Better Future," we work on various fields. However, we have a strong focus on additive manufacturing and 3D printing that I will talk a part of it today. So starting on the history of construction, so starting on the ancient buildings where we usually built in stone, in masonry, in wood. These were the main construction materials from the past, and at that time we also used simple construction techniques like wooden auxiliary constructions. Then we came with the steel. The steel provided us the possibility to build a bit more complex structures, allows us to build steel railways. Then we received the concrete, and this is a past history that the goal was, or the challenge was to build safely. And then there was not so much, but there was some introduction of some technology like the using of cranes, the using of lifts that allows us to build skyscrapers. So a little innovation, but as someone already said today, the construction itself, it's not so much industrialized sector. And there is now the recognition that it is needed more industrialization, more technology. And that's the challenge that we have from here on. And also not forgetting that we have to do it now in a sustainable way. So words like ecology, energy saving, sustainability, digital are the words that we have today for the future. So this is very present on the 17th Sustainable Development Goals that were established by the United Nations for the 2030 agenda. So these goals are in a broad sense. I can particularize some of them that are applicable to our industry, like greater adoption of clean and environmentally sound technologies and industrial processes, like 3D printing, for example. The other one, it's by 2030 to ensure access for all to adequate, safe and affordable housing and basic services and the upgrade slums. I think the new technologies that we have will help us to achieve this goal. And also the efficient use of natural resources. It's another example of the 17th Sustainable Development Goals. And this is closely related with materials. When we talk about materials, usually we remember of the three big kinds of materials that we have in construction, like concrete, steel, and wood, which are the main structural materials that we can use on building. You can find several studies on the literature that compare these materials. That's not the goal here. I just want to say that the sustainability of these materials depend on some key factors, like the use of local materials, the service life, which comes together with durability, the availability, the end of life disposal, which means if we can reuse, or if we need to dispose some kind of material, and also about the energy source. I mean the energy that is used to produce some kind of material. So this is the huge goal, the improvement, the optimization of the sustainability regarding the kind of material that we want to use. And also there is some environment concern. I have here some examples about waste materials. Waste materials are nowadays a concern. There are a number of industrial wastes that we need to look and see where we can use them in the construction instead of landfilling. So one of the examples that we are using on our research is the biomass ashes that are used in Portugal. 90,000 of tons of biomass are produced per year in Portugal. Another example is the rice husk. The rice husk, for instance, the rice husk ashes proved to be a good material for construction already. So we can use rice husk in construction, the ashes, I mean. about 7 to 18 millions of tons are produced annually. Stone sawdust in the center region of Portugal, we have a huge industry on stone sawdust. I mean, stone production and the wastes that are created by this production are very huge, 155 million of tons per year. So it is a huge amount. Also fly ashes from coal. Also there are, it is a world concern. And another example, and the last example, are the construction and demolition wastes. Which, as was said before already, only 28% of it is recycled. So there is a huge need of using this construction and demolition wastes on construction. So one answer to this will be not only, but could be the use of geopolymer cement. Geopolymer cement can be one of the solutions for this problem, not the only one, of course, but one of the solutions. We are researching on the geopolymer compositions. The geopolymer composition is composed of precursors and alkalination solution. The precursors can be from wastes, like fly ash, like blast furnace slag, like mine tailings, stone sawdust, glass wastes. So these are kind of waste materials that can be used to formulate the geopolymer cement. The alkalination solution is then composed of sodium or potassium hydroxide or silicates that together make the geopolymer cement paste. And with this geopolymer formulations, we can achieve some waste reintegration, leading some management alternative, creating products that contribute to a circular economy. And also in the part of the materials, meet some targets from the global consensus on sustainability in the built environment, namely reducing the environmental impact and contributing again to the circular economy. Here I presenting some numbers that you can find on the literature about the geopolymer cement. You can see that the mechanical properties, physical mechanical properties are comparable to the Portland cement. Of course, this depends on the formulation. These are some values that were taken from the literature. Of course, this depends on the formulation. We can get more or lower performance depending on the formulation. And here the formulation is very important on the geopolymer because it can be very different depending on the waste material that we use. However, these numbers tell us that the performance can be similar, also can tell us that the environmental impact can be lower. We are not, of course, talking about replacing Portland cement. Of course, there is, as already was said before, there is a need of reducing the Portland cement. Maybe we have to use it in some amount, but the geopolymer cement can replace some of it. And these are some results of some cement pastes. So here in this table, I am showing you the paste cement material, so without aggregate. And here you have the results of the use of mine tailings, construction and demolition waste, and limestone powders in geopolymer formulations, where we get strength between 40 and 50 megapascal in compression. So it's very interesting results. In here, in this table, some results on cement mortar. So in here, using aggregates. We can see also some interesting results using waste ceramics powder, glass waste powder, biomass fly ash as the main precursors, and we got a very interesting compressive strength. So as I told you, these results, and these are results from some laboratory results of us using methacholine on the formulation, where we got 45 megapascal in compression and 10.5 megapascal in bending strength. So these are results that give us the opportunity to think about the use of geopolymer in the construction, of course, without forgetting that there are some challenges. That's why we are working on it. And one of it is the special handling. So the hydroxides and silicates used are of special handling. So in the application in the industry, these are things that have to be taken in account. In addition, the use of raw materials gives us an additional challenge, because as raw materials, as waste materials that we use, they are variable. They are very variable in the composition, and so the formulations are more difficult to establish. And in addition, the geopolymerization mechanism, it's not completely understood, so we have to keep studying, keep researching on the geopolymerization mechanism, and mainly in the part of applying it in the industry. And of course, the application of this technology in the construction industry. One of the things that we see is that in the construction industry, we usually are very conservative, and so the introduction of new products, new technologies is not easy. So that these are things that we have to take in account in the implementation of geopolymer cement in the close future, and we are also searching for applying it in 3D printing. Another example of the use of sustainable materials is that I want to bring to you is the use of the insulation materials, greener insulation materials. In here, I show the embodied energy of some insulation materials. You can see that cork, for example, has a very low embodied energy compared to glass wool or rock wool, but also very low compared to polystyrene, for example. So in fact, we are using insulation materials to save energy, but for warming, for example, but then we are also using materials that have high embodied energy sometimes. And so our research, it's also about the use of agricultural wastes or forest waste in insulation materials. In here, I show you insulation materials which is composed of moss, and you can see by the graphic that the thermal conductivity it's in the range of the results of the usual thermal insulation